Okay, good morning. We can start the session. Our first speaker is Professor David Mason. I think talk on fluid pressure.
Well, thank you very much. Thank you for inviting me to give a plenary talk. This will be on hydraulic fracture. Can we have the next slide, please? Now, just an outline of the talk. We'll give some examples of rock fracture by high pressure fluids, and then we'll look at the bulk fluid model, which can describe both laminar and turbulent flow in the fracture. And then we need a model for the pressure that keeps the fracture open. The two models we'll look at, the PKN model, and then an elasticity model, and then a similarity solution. So get the next talk. Next one. Now, some examples of fracturing rock by high pressure water. The first case is, can we fracture rock using high pressure water instead of explosives? Explosives create small particles. All sizes of particles, especially dangerous, are particles of a certain size because they go into the lungs of the mine workers, the miners, and they stay there permanently and lead to a lot of potentially fatal mining diseases. This problem, actually, we run a mass and industry study group in South Africa each year, and this was a problem submitted in 2004, and we found the rocks were, the gold mines were very hard rocks, and it wasn't really practical to do that. But it led to a whole program of interest in hydraulic fracturing. And another important area is geothermal reservoirs. This occurs at places on the earth where the crust is quite thin. They pump cold water into the fractures. This is below the surface. The hot rocks heat the water, and the hot water is extracted from the ground and used to generate electricity. And an example in Africa of this is the Great Rift Valley in East Africa. For example, Kenya has got over 40%, about 47% now of its electricity is generated by hydrofracturing. This method is clean and sustainable, and it's consistent with the transition to renewable energy and clean energy. If we can have the next slide, this gives an indication worldwide of hydrofracturing. The US, the United States, for example, this shows the increase from 2007 up to 2019, and of course there's been further development since then. The largest capacity is in the United States, but that represents only 0.3% of the national generation. Other countries, Philippines, quite interesting. That corresponds to 27% of the generation of electricity. Now, New Zealand, we know about the Rotorua and the hot springs there. That's about 14% of the electricity is generated from hydrofracturing. Now, in Kenya, we've got 38% in 2019. It's up to about 47% now. So it's very important in East Africa. Other areas, Costa Rica, and so on. So can we have the next slide? This shows a map of Africa and areas with high potential, not exploited, but of high potential. And starting in number one's northernmost Africa, and then two, the Gulf of Suez. And then
Screen.
okay. And an important potential area is Ethiopia. Ethiopia is here. This is the start of the East Africa Rift Valley, all down here. Not much is done in Ethiopia, but it's got the same potential as Kenya. And this is Kenya here on the Rift Valley. The Rift Valley seems to sort of branch here into Uganda and then into Tanzania. Even northern Malawi. This is Zambia, has got some potential. I was very interested to see that in the Cape, the border with Botswana and South Africa got some potential. This is the where Kimberley is. The igneous intrusions have got the diamonds, so there must be, the crust might be quite not deep there, and even in Namibia. So there's lots of potential for hydrofracturing generation of clean energy in Africa. So the next slide. Now, another application of hydrofracturing is magma-driven propagation of cracks in rocks. This is just natural. The magma flows into the cracks, and it's responsible for the dikes. They are vertical intrusions, and the sills are horizontal inclusions. And this magma needs to be injected rapidly to prevent solidification. So there's nice problems here for students to work on. The magma is flowing in and cooling down and solidifying. This is quite nice. Hydraulic fracturing. This is a sort of contentious area. It's the release of natural gas and oil trapped in shale rock. South Africa's got the 8th largest reserve in the world in the Karoo of shale gas and oil. But the Karoo is a very sensitive conservation area, and there are substantial economic and energy benefits for South Africa, but there's the potential for adverse impact on the environment. And about 15 years ago, the Royal Society of South Africa was asked to investigate whether we should mine the shale oil and gas, and they came to the conclusion that South Africa should not mine that gas. The bottom line is the oil and gas, they're fossil fuels, and trying to move away from fossil fuels. So the next, this is an example of hydrofracturing by magma. The interesting point is that it moves up. The fracture can develop in both directions with the source maybe at the center here. We also have fractures in one direction. This symmetry is quite useful mathematically, in deriving fracture laws for the rock. The symmetry helps with the derivation of these results. So next slide. Now, we'll say something about the model. It leads to an interesting nonlinear diffusion equation and other types of problems. And just to see on the assumptions that the model's based, because we do a lot of work in solving it, we should really check the model itself, the assumptions made in the modeling. The fracture is very thin, so thin fluid moving between two rock interfaces. So we use lubrication theory. We neglect inertia due to large velocity gradients. Because it's very thin, there's a very large velocity gradient in this direction. And the viscous stress is the viscosity times the velocity gradient. And even although the viscosity might not be large, because the velocity gradient is so large, then it will dominate inertial terms. Now, we said that this model describes both laminar flow and turbulent flow, and that is because we average the velocity over the half width. So instead of depending on t, x, y, we average out the y dependence and we get a function only of t and x. So that would allow us to look at turbulent flow as well as laminar flow. And we average the pressure over the fracture. So we work with a mean pressure in the fluid. Now, the wall shear stress, this is the fluid is viscous, so it sticks to the fracture walls. And we need a model for that shear stress. And it is based on experimental work done by Blasius for smooth wall turbulent flow. It's known as Blasius's friction law. We know of Blasius because of his boundary layer solution flow on a flat plate, the Blasius differential equation. But he also did important work on turbulent flow. If we can see the next slide, this next one, this is very dark. This is taken from a paper on the life of Blasius, life in research and education. This is the wall shear stress is vertical here, and the Reynolds number is horizontal. It goes from 5,000 up to 200,000. And you found a straight line dependence. The gradient of the straight line, the Reynolds number to the power -1/4, the negative slope. And this was really a surprise. This was 1912. No one thought that turbulent flow could satisfy a law like this over a large range of Reynolds number. And so this equation that we get for turbulence, it's based on experiment. So that's quite good to have something based on experiment. Now, this is for smooth wall fracture. There's also rough wall fractures. That's a different case. This is a smooth wall tube. So if we can look at the next slide. This is a photograph of Blasius after retiring in 1962. He made important contributions. You know, the first solution of boundary layer equations, his work on turbulence. He also did work on aerofoil and separation of boundary conditions. He did all this in about 6 years. And then the rest of his career, he spent in lecturing and teaching. So, go to right. Now, so this is the Blasius's relation between the wall shear stress tau naught and the mean velocity Vx bar and the half width h of the fracture. And we put in a parameter m here Now for the turbulent flow, smooth wall, turbulent flow M is -1/4. For laminar flow, is the stress is just proportional to the velocity gradient. M is equal to -1. And then an upper bound for rough wall turbulent flow, M is equal to 0. It was about 25 years after Blasius did his work on smooth wall turbulence that they began to understand rough wall turbulence. So his work was ahead of the time. In the same, his boundary layer solution for a flat plate was about 1908 or so. It was the 1930s, about over 20 years later, that boundary layer theory was applied to the free jet. So again, his work, that work with Blasius and Prandtl was sort of ahead of his time, and got a big gap between the next contribution. It shows it was very original work. So we can go to right now. This is Cauchy's first law of motion. All the equations of the in continuum mechanics are derived from this, and we've said that the turbulent, the viscous stresses are much more important than inertia, so we neglect the inertia on the left-hand side. And we've just got a balance between a pressure gradient acting on the fluid element and the wall shear stress, tau naught. And they balance, and we get this simple equation with inertia neglected, relating the pressure gradient H and tau naught. And then another slide, please. Conservation of mass. Mass is conserved both in laminar flow and turbulent flow. Must remember that mass is conserved in turbulent flow. This is a velocity. We know the y component of velocity is just the rate of change of the half width. This is the total derivative, but interestingly, when we expand the total derivative, it depends on the x component of velocity at the wall, and the no-slip boundary condition gives that 0. So it's just equal to the partial derivative. And then we integrate conservation of mass across the fracture with respect to y. The y derivatives just give the velocity at the upper and lower surfaces, and then this integrates to our mean velocity that we're working with. So we get a relation here between the mean velocity and the half width. So that's another equation that we've got. So if we can go to the next slide, please. Is it, oh, it takes time. Oh, right. So sorry, we've got the next slide. Now this is the three equations that we have. We've got four unknowns: tau naught, pressure, average pressure, the average velocity, and the half width. So we've got three equations for four unknowns, and we're interested in the solution for the half width, and we can derive from these three equations one equation relating the half width h to the mean pressure p bar. So this has got the form of a diffusion equation. But to complete the system, we need another relation, and that sort of makes sense. We haven't said anything about the surrounding rock or the force required, the pressure required to keep the fracture open. Now, the net normal stress which keeps the fracture open, we denote by capital P. Now, we're looking at a rock mass below the surface. So we've got compressive stress acting on that. and we've got the mean fluid pressure inside the fracture, keeping it open, and the resultant pressure, which will keeps the fracture open, is the difference between the fluid pressure in the fracture and this mean normal stress acting outside. And if this is positive, then the half width will grow, and if it's negative, the half width will decrease. So this is the important quantity here that we need to now model this and get a closed system. So there are two models that are used. So if we can have the next slide. Now, one model goes back to the 1960s and early 1970s. It's called after Perkins, Kern, and Nordgren. And it's called the PKN model. And it's assumed that this net pressure that keeps the fracture open is proportional to the half width. This is the simplest model that, no, we need to, we'll have to go back. Yeah. Right now, so that converts our equation into a nonlinear diffusion equation. And a lot of work has been done on that. And we'll look at some work we can do using these symmetries and conservation laws. So a lot is done on that. It's the simplest model. The next model that was introduced, this was in 1985 by Spence and Sharp in Proceedings of the Royal Society of London. Now, from the theory of fractures in plane elasticity, plane strain, and using complex variable theory, the can derive a relation between the pressure in the fracture and the spatial gradient. And this is a Cauchy kernel here. It's singular when s equals x, so this is a principal value integral. Now, this is now used quite a lot in this work, and it's not usually referenced who was the first to derive this. I think that's an ultimate compliment to the person that his work is used so much they've stopped referencing it. But I think it could go back to Barenblatt, a Russian or Soviet mathematician. I've seen a derivation by Barenblatt. I know that he did a lot of work on the stress intensity factor in his book. We'll discuss that later. Spence and Sharp were the first people to apply this result to hydraulic fracturing in 1985, and then they produced an approximate solution. David Spence was in fact my PhD supervisor. It's over 50 years ago now, in 1960. He did this work later. One day he came in and he looked very happy, and he said, "Now I've got 2 tickets, rugby tickets, to see the All Blacks, playing England at Twickenham." So I'd always thought that Spence was English, and to be quite careful here, I said, he asked me if I knew who the All Blacks were. Remember, this isn't South Africa, this is back in England. And I said, yes, it's the New Zealand rugby team. So he was very impressed by this. So Spence actually comes from New Zealand. He's a New Zealander. And we saw that New Zealand hydraulic fracturing is geothermal fracturing is quite important in New Zealand, and maybe this is where he developed an interest in it. So we've got this coupled system of integral differential equations, quite difficult to handle. I don't know if any Lie symmetry analysis has been done on this. We'll look at a simple scaling transformation, but I think that this is an area, I'm not sure if Lie symmetry analysis can be applied to problems of this kind. So we'll first look at the PKN model. Now, I was very interested in the plenary lecture yesterday with multi-reduction of equations of this kind. We'll apply the double reduction method. I didn't know about the multi-reduction method. So I think it's got lots of potential on this problem. So we'll discuss the double reduction solution of this problem, and we'll see the sort of difficulties that that can lead to, and why the multi-reduction method would solve all these difficulties. Now, right, that stage by dt. This is the diffusion. Oh, this is wrong. Yes, thanks, misprint. Thanks a lot. Thanks. Right now, so now the Lie point symmetries of this. This was derived by one of my students about 10 or 15 years ago, Anthony Raja. It's quite a nice result. This was done by hand. You can still do this by hand. It's not too complicated. And it's quite nice result for the Lie point symmetry, quite a concise result. It depends on 4 constants, C1, C2, C3, C4. So we'll work with it with all 4 constants, but that would be 4 Lie point symmetries. But we'll work with this combined one and see what values we can assign to these constants. And then we can get the invariant solution by the usual approach, operate with the Lie symmetry on that. And then we end up with a first order PDE. That's it's a linear first order PDE. And we solve it in the usual way, and we get an invariant solution. Is it moving? Yeah. So this is the invariant solution. Depends on time times an unknown function of xi, and where the similarity variable is essentially x upon a power of t to the power c4 upon c2. Now, when we know the back, when we substitute this into the PDE, we get this ODE. So this is the ODE. And we immediately see if C2 upon C4 is 5 upon m plus 2, then this is going to be integrable. We can integrate it, and at least once we don't know if we can integrate it further. And the question is, what other values of C2 upon C4 can this be done? Are there other values that we can integrate this equation? Now, we use the double reduction theorem. This was a special case of the work discussed yesterday. This was by Astrid Stroberg, who is a student of Faisal Mohammed. Astrid showed that if a partial differential equation is reduced to an ODE by a Lie symmetry associated with a conserved vector, then the ODE can be integrated at least once. So what we've got to do now is to look at the conservation laws for this equation. And this is the conservation law. And once we find them, we'll associate them with the Lie point symmetry and determine, we can investigate if there are other values of these constants for which this can be integrated. This is the total derivatives in time and space. And the conserved vector is just the components T1 and T2. So right now we use the multiplier method. Just to revise what we do, a multiplier times the PDE. We expand the PDE out in terms of partial derivatives, and if we multiply it by the multiplier, it puts it in the form of a conservation law. And we look at this for all functions H, which is important, not just for solutions for the PDE. All functions, so that the partial derivatives are independent. They're not necessarily connected by the PDE. And then we operate with the Euler operator of this form. Professor Blumen visited WITS about 15 years ago or so, and told us about the multiplier method, and started using it. And I was wondering, is there a 2 in here? And so Professor Blumen was still there. He was in his office that we'd signed to him for 2 or 3 days, and I went up and said, now should there be a 2 here? And he said, no, there's no 2. Yeah. So always remember that. Now, the Euler operator annihilates these divergence expressions, and the conservation laws you get depend on the form of the multiplier we take. Now, we were doing this by hand, so we took the simplest form, a function of t, x, and h. But of course, a multiplier can depend on the first derivatives, second derivatives, and so on. But it gets more complicated the more functions you put in there. This is it's not too difficult. It's quite comfortable to work with that by hand. Otherwise, you have to use programs. So we found the multiplier. No, this just gives an example of some of the expressions that you get when working by hand. I've put it up here just to sort of say now the mass doesn't know what's turbulent and what's laminar. Is laminar or turbulent flow coming out in the mathematics? And we see that, remember, laminar is m+1 is 0. We get a lot of m+1s up at the top here, and m+1 here. So clearly, laminar flow is going to be different from the general. There's no m plus a quarter here or anything like that. It's not picking out a specific turbulent flow, but clearly laminar result is going to be different from the turbulent result. And so the laminar result, the multiplier is AX plus B. So there's going to be two conserved vectors, whereas for turbulent flow, laminar is equal to B. And a student who was working on this came and told me that we've lost a conserved vector in turbulent flow. So when a student tells you that, either it's a big breakthrough or there's an arithmetical error someplace. So I checked that all the input was correct. We lose a conserved vector for turbulent flow. Laminar flow has got two conserved vectors. So now what we do is we've got this equation is we put this in conserved form, and this is true for arbitrary functions h. At this stage, we insist that h is a solution of the PDE, so the left-hand side will be 0. And this gives you a conserved, the conserved vectors. It's in conserved form. So we see the conserved vectors that we have. So if we can go on, right? So the conserved vectors for laminar flow, m equals -1. There's the elementary conserved vector. There's this new one here, new conserved vector. And for turbulent flow, we've only got one. It's the elementary conserved vector. One can see this from inspection. And we'll see the physical significance of the elementary one. And it's interesting to see the physical significance of this one. So that's with multipliers, just a function of t, x, and h. If you use more variables in the multiplier, you might find more conserved vectors. Now, right, so if we can. Now we've got to associate a Lie point symmetry with the conserved vector. From the papers by Kara and Mohammed, around about 2000, two papers, they introduced this expression for the condition for a Lie point symmetry to be associated with a conserved vector. And this splits up for the problem that we are, the two-dimensional problem, two components. So we've got to substitute the Lie point symmetry into both of these components. X infinity, we just prolongate x to the required amount, depending on the partial derivatives that T1 and T2 depend on. So this equation is due to Kara and Mohammed. Now, so we can get the next one. Right now, so we've got our Lie point symmetry, and we associate it with the conserved vector. Now, this is true for both laminar and turbulent. This is the elementary one, and this is associated with the Lie point symmetry, provided C2 upon C4 is 5 upon m plus 2. That's the result that we saw just by looking at the ODE. Now, this conserved vector is associated with the Lie point symmetry, provided C2 upon C4 is 8. This is a new result, and it doesn't depend on m. If we can, oh, we got it right. So now this is our ODE. I've just tidied it up by renaming just transforming the variables a little. So this is the ODE, and they're the boundary conditions. This says that at the fracture tip, the half width is 0, and the flux of fluid is 0 at the fracture tip. They're the boundary conditions. Now, this is the ODE that we solve. We can see an example of Astrid-Stroberg's double reduction theorem, that we can integrate this once. And it turns out that we can integrate it completely. And we end up with this result. This is the physical significance of this is a fracture evolving with constant volume. We've got this fracture, no fluid is entering or leaving the fracture, and as the length increases, the breadth will decrease, the half width will decrease, such that the volumes are always conserved. And this is true for laminar and turbulent flow. Now, the second solution for laminar flow, when C2 upon C8 is equal to 8, then we get this ODE. Now, we know from the double reduction theorem that we can integrate this at least once. It doesn't tell us how to do it, but the work we saw yesterday explained how we can proceed further. So this is one difficulty in this. You've got to integrate this equation. There will be systematic methods of doing that. I'll show you one that's just an ad hoc method to integrate this equation. But this is the solution that we get. U to the power 4th, then this solution. This is a new solution in hydraulic fracturing. And what does this describe? It's the limiting case of fluid extraction. We think of putting fluid into a fracture. This is extracting fluid from a fracture. We saw in geothermal fracturing that we do extract fluid at the end and bring it up to the surface. Now, in this solution, the volume does not remain constant because it's the other solution's constant volume. So the volume of this fracture is decreasing, yet the fracture is closed at both ends. And essentially, the flux, the average velocity tends to -infinity, and the half width is closing, and they're doing that at the same rate, so that there's a net flux at the end, even although this is closed. I think applied mathematicians appreciate this, but it's difficult explaining this to engineers. Anyway, you got the fluid extraction out of this fracture and is evolving. And to look at the fluid flow inside is quite interesting, because there's a dividing line. Part is flowing in this direction as it escapes, and the other part is flowing in this direction because the length is always increasing. And you can analyze the flow inside the fracture. That is quite an interesting solution. So there are also the limiting cases, which is quite interesting, that the theorem brings up limiting cases. It's not some sort of intermediate case, it's a limiting case. Now, just a quick outline how one can integrate this equation subject to these boundary conditions. If we multiply this equation by u, this might even be a multiplier. You multiply by u, and then we can combine these two terms here. as this. We've got to take this u here and put it inside here and subtract off something, but what we subtract off can also be integrated. So we then end up with the first integral of this. The question is, can we integrate it further? That's as far as the theorem guarantees. Can we integrate this equation now? And divide by 1/1 UG, we see that we can write it as a first order ODE in G cubed. So we can integrate this equation and get an exact solution. But that wasn't guaranteed by the theorem, as Astrid proved. Now, the elasticity model, this is the fluid fracture. It's a symmetric model. We saw that that's quite useful and it's quite realistic in geophysics. The fluid is expanding in both directions. And we've got this coupled system of equations. Capital P here is given by this integral form. You can keep it as a system of two, or you can put it inside there and have an equation for H. And it's Cauchy principal value integral. Now, in the paper by Spence and Sharp, they showed that a similarity solution could be derived for that paper. It was a bit of a surprise at that time that something so complicated had a similarity solution. Now, we've got to say something about the elastic theory of crack propagation. This is described in Baron Black's book on fractures. You see, we've got a singularity at the fracture tip. Now, it makes sense that there must be some measure of the resistance to the fracturing by the material. This is referred to as the toughness of the material. And if we look at X tending to the length from outside, we find that P tends to this expression. It's got a singularity to the power of half. And the toughness of the material is defined as this, this expression. When we come to look at the similarity solution, we'll see why we need a third equation mathematically, and it makes sense physically that we need to have some measure of the toughness of the material we're fracturing. So we've got the diffusion equation, the singular integral, and the toughness. And we'll look at a similarity solution for these three equations and use the scaling transformation. This is described in Dresner's book, Similarity Solutions, about the 1980s or so. And I found this is actually very useful to do this before doing a symmetry analysis. If this admits a similarity solution, we know at least we've got a scaling symmetry. So if we do that, then we see on the left-hand side the powers of lambda. Now there are four. There was A, B, C, and R, and we get these three conditions for these equations to be invariant under the scaling transformation. And in this work, it's not the actual values of A, B, C, and R that's important, it's a ratio. the ratio of these to one of the values. And we take the ratio, we suppose A is non-zero, and take the ratio with A. So we've got 3 unknowns, not 4 unknowns. And we've got 3 equations, non-homogeneous, for 3 unknowns. And now we see why we needed to add something about the stress intensity factor and the toughness of the rock to get 3 equations for 3 unknowns. And this can be solved, and we get specific values of the ratios, which are independent of M, which is quite interesting. Although M occurs here, the actual solution is independent of M. So this is the similarity solution. Essentially, how do we get the invariant form from this? Is described in Besner's book. We look for a solution as a function of t and x. Then the transformed equation will be a function of t bar and x bar, but the same function. There's no bar in f. And just putting in the transformation, differentiating this with respect to lambda, and setting lambda equal to 1, then we get a first order PDE for f, and we can solve that, and we get the form of the similarity solution. So now, so we get the general form of the similarity solution. This was derived in the paper by Spence and Sharp. And it was a big step forward at that time. Interestingly, how do we get the length of the fracture? Now, we can get the length of the fracture without solving the ODE, the time dependent, because the fracture must vanish. The half-width must be 0 at the end of the fracture. So we put in the similarity solution. If we write that in terms of the similarity solution, this must be true for all values of WT. And you can argue that WT must be a constant, but if we differentiate this with respect to time, we find that since f isn't a constant function of w, the w by dt must be 0. So WT must be a constant, and the similarity variable is just length, is k times t to the 2/3. So we see that this fracture grows at the rate of time to the power 2/3, but we don't know what that constant is. We get that, we've got to solve the problem. But for free, essentially, we get the rate at which it expands with time. So maybe if we can, I think I've run out of time almost.
No, you still have 8 minutes.
8 minutes. Okay, then. Right now, so this is the invariant form. This is the ODE now, and this is the pressure expressed in the similarity variables. There's an important quantity, the flux of fluid flowing in the fracture, and that is related to h cubed and the derivative of the pressure. And all these are is written as ODEs now. If we can have the next slide. Just mentioning the boundary condition. F vanishes at the end of the fracture, 0 flux at the end of the fracture. Now, this is the total volume, just the integration along the fracture. If we put in the similarity solution, we see that the volume of this fracture increases like t to the power 1. We don't impose that. This comes out of the similarity solution. Increases like t. So the rate of change of volume is the flux. There's the 2.5 there because it's standing in both directions. And this is another boundary condition. The flux at the origin, the input of fluid. And we rename the similarity variable, divide by K. And then if we see the next slide, we've got this similarity solution along the top here. The K has been taken out of the limits and put into the variables. This is the ordinary differential equation that we've got to solve, where K is related to this Cauchy integral, Cauchy kernel here, and this is the toughness. Approximate solution, maybe if we go back. So approximate solutions have been derived for this, but I don't know if any Lie symmetry work on this. I don't know if it can be done because of this integral person who applies methods. I don't develop the theory of Lie symmetry analysis.
Yeah, this is developed.
Sorry?
It is developed, it's possible.
It is okay. That's good. Because it sort of makes sense that we got a scaling symmetry, scaling transformation, which would imply that it makes a scaling symmetry. Let's see. Anyway, that's I'll comment on what's been done in this. We use asymptotic methods. Maybe the next slide now, please. Thanks. Approximate solution was given by Spence and Turcotte, and this is quite useful when comparing numerical solutions. You know, you expect an approximate agreement. This is a very good paper by Fitt, Kelly, and Flees on geothermal energy reservoirs. I mean, this is older work. I'm just describing some of the older work, and Sarah Mitchell, Kuska, and Pierce. Anthony Pierce is a South African. He's working in the University of British Columbia in Vancouver. He's got a group working on hydraulic fracturing, and they worked matched asymptotic expansion methods, both for porous medium and with no leak off. And the next slide. And then Adachi and Pierce also developed that analysis further. And there's been quite a bit of work done since then. What's quite interesting is the numerical methods. We saw that there's a Cauchy kernel, and how does one handle that numerically? And through these problems, at least at BITS, we're looking at numerical methods for that. And one of our former students with Gideon Fario, they published a paper on the similarity solution for a pre-existing fracture in permeable rock. The Cauchy kernels come up a lot in problems in applied maths. We tend not to discuss them in numerical courses for undergraduates or honors students. I think they're quite important, and we've been bringing them into honors projects rather than the lectures, but might be included in the lectures. I think Matabelli might be speaking tomorrow on his work at this conference. Yeah. Okay, then, thanks very much.
We still have a couple of minutes for questions.
Very interesting talk.
Yeah.
I'm trying to understand. So in the mind, The question is for them to go deeper. These are gold mines.
Yes,
The
yes.
application to, oh, sorry, yeah. To dig deeper, right? Or to go, so they're going deep down and trying to find possible gold. They
No,
are. What is it?
the mines, the cracking was sort of a health issue, so that the small fragments of rock didn't affect the miners' lungs.
Okay, so this is about, so what's the idea? Is it to?
Now, this hydraulic fracturing is from the surface, you force fluid down under pressure, and then at a certain depth, it moves horizontally. And there are already fractures there, and it opens up these fractures, and then the gas and oil is extracted because the fractures are opened up. And it's
All right, then
to
it's
the
safer for the
surface.
miners.
Well, that's a very good point.
Is that what it is?
Yes, and it's very disappointing that this method sort of has run into problems, because instead of miners going down and, you know, a lot of fatalities and losing their limbs and everything's done from the surface. But there's problems with, got to be careful about the groundwater, but they could, I mean, the groundwater that we extract is about 500 meters, maybe at most, from down from the surface, whereas the hydraulic fracturing is done about 1,000 or 2,000 meters, much deeper. You just got to be careful. Maybe you surround the tube by some protection that it doesn't leak off into the groundwater area. But as I said, the basic problem is that it's fossil fuels that you're extracting. But in geothermal reservoirs, there isn't that problem. What they do now in the mining to prevent these particles entering the miner's lungs, the shift goes down and puts the charges in. Everyone comes up to the surface. They then they ignite the charges, and all the explosions take place. Let everything settle down, and then so many hours later, whenever it's safe, the miners go down and then extract the ore. So there's no miners down now. They are down when they do the blasting underground.
So do the industry partners, the people you're working with, so when you find these results, you share with them, right? Because we had a recent explosion in Johannesburg where people got killed, and they said it was accumulation of, is it gases? Is it methane gas?
Yes. Yeah, well, that was along one of the streets, Bree Street. It could be that some of the exits for these gases were sealed off for security, and the gas accumulated underground. One person noted that you know, we have power outages, and this explosion occurred just after power was restored. In other words, there might have been some sort of spark or something as a result of that. So there's all sorts of different theories, but that's not deep down.
May I ask one question and one comment? You talked about Barenblatt.
Yes.
Actually, Barenblatt, he was a student of Sidov. So, and his book about dimensionless analysis.
Yes.
So this is 1948, maybe, right? First edition. And this is another one. I didn't want to say about that, you know, this book. I want to say that Barenblatt, he was a student of Sidov. And Ovsyannikov, Lev Vasilyevich, he gave a seminar in Sidov seminar. And Sidov, he asked Barenblatt, can you do these solutions? It is from Ovsyannikov. He told that, he asked Barenblatt, can you do? No. Can you do? So that Ovsyannikov, he presented the applications of group analysis. So more general than dimensional analysis. So this is just common. And question one is about the following. You have four-dimensional algebra. And four-dimensional algebra, all four-dimensional algebras, they are classified by Patera and Winternitz. So then you have many constants. Why you don't use optimal system to get rid of these constants?
Well, I can. I don't know how to use optimal systems. Well, I know. Yeah. I don't, that's right. I know some of the students do that and classify everything. Yeah. I allow the physics to take care of itself.
Because it's done already by Patel in 1972.
Yeah, yes, yes, okay.
It's not missing. anything, do it.
No, he told about constant, how to choose this one, but it's possible to make it. And to find all possible values.
He's essentially done.
No, he did not follow them.
Yes, he did.
That particular.
No,
He told, he threw over, he five, or he four. Something
we
like
can
this.
talk later. Optimal systems will not give them any.
Don't know.
Yes, I do.
Oh. Oh,
Because here, it's not possible. Because my particular.
We give him the general generator, so he hasn't missed anything. We can.
No, after the key was condition, so some.
It's not necessary.
No, it will take up just a bunch of things like that. Particular case,
It's what we can discuss later.
okay.
oh, thank you.
Yeah, I just have an announcement. David, I'm not
Yes.
sure if I should announce this here. That there will be some kind of colloquium in your honor next September
Yeah,
at Wits. So
yes,
please,
okay.
people, keep that in mind.
Yes.
I'm not, should I say about why it's,
Well, yes, you.
well, David is going to be a bit younger next year. So with this colloquium is in his honor for the. Shush, I don't want to say numbers. Okay.
It'll be
just-
my 80th birthday if you.
So-
Yes, yeah.
Yeah, well, David's going to be it's for your 80th, right?
Yeah, well, it's the fourth time I'm 20. That's-
So it's an invitation to participate. And you can.
But for now, it's September. I think the first week.
Thanks. Uncle. Oh, okay.
Nice talking.
Oh, good, thanks. Are you sure?
Yeah, I need to run up.
Okay.
I will leave this with you.
I just, yes, yeah. Maybe, okay, maybe if you, that's fine, thanks. Yes, yeah. Thanks. I can help you. I can help you. Okay.
Okay, so we're ready now for our second talk. Dr. Macaulay on toward extended unified method solutions of partial differential equations and nonlinear wave configurations.
Okay. Firstly, I speak about my presentation toward extended unified method, exact solution of nonlinear partial differential equation and the nonlinear wave configuration. Contain about outline of extended unified method. Also, two examples, two types of a solution, polynomial solution and the rational solution. And two example was about NV equation was time dependent coefficient, and also with the YTS equation with the space time dependent coefficient. First, nonlinear partial differential equation have a variety of important rules in describing many nonlinear phenomena in science and engineering. Also, there are many powerful methods already described or find the exact solution, as the G over the GGS method, exponential method, tangent method, sine Gordon method, also Jacobian method. Question 1.1 is the general describe for nonlinear partial differential equation with dependent and independent many variable. Here we speak about a unified extended unified method. Are classified polynomial. This method classified two types of solution: polynomial solution and rational solution. Also with auxiliary function phi function space and time also. First, polynomial equation. Polynomial equation, we describe solution, take the formula, two dimension space and time as power as order n. Also, auxiliary equation power p also of order k. So I must right. U summation CJ phi for G is 0 here. That's the main idea of method about power of polynomial power n, also order n, power of auxiliary equation p take two types, 1 or 2, also power of auxiliary equation. So this method depends on two numbers b, k, and n. Also, n and k have a relation between balance between condition between higher derivative and nonlinear. So relation between n and k depend on higher derivative, balance between higher derivative and higher derivative and linear term of nonlinear partial differential equation. Also, our rational as this example of when take p equal 1, so power 1 and k equal 2, so polynomial order 2, so phi dash as polynomial order 2 when t p equal 2, k equal 2. So at another formula of auxiliary equation, phi dash power 2, so phi dash take the two formula, maybe given a soliton wave, maybe to give elliptic wave solution. Okay, rational solution also depends formula of U is a rational solution with the same value of auxiliary equation. The change also in formula of solution replaced by polynomial solution to be rational solution, numerator power n and the denominator power r. First example we face up is we speak about the self-similar traveling wave solution 2 + 1 dimension for NNV equation with time dependent coefficient. NNV equation with time dependent equation has this formula, this nonlinear the partial differential equation was high with three derivative and nonlinear term. First, we omit this integral by taking Vx equal Ux equal Vy. So equation 1, 2 become equation 2, 2 couple of equation 2, 2. First, we search to find the polynomial solution and the rational solution for equation 2, 2, 2, 2. Also, before we start, this is the main term of equation. So when I use my method, so I want to take P equal 1. So relation between K and N in this equation from this two term N equal to K plus 1, because this term is N plus 3 K minus 1 to N plus K minus 1. So relation between K and N from this term is N equal to K minus 1. Also order V equal order M. The formula of polynomial solution, we take the transformation Ux Yt to be U capital Xit. So with transformation 3 dimension to be 2 plus 1 by dimension to 1 plus 1 dimension. XYZ to be Xit. This formula of Xi as similarity transform from X and T equal T. So from equation 3.2 to equation 2.2, we find this equation 4.2, this transformation for the last equation. The equation is 1 plus 1 partial differential equation or linear partial differential equation. Polynomial solution depend on when take B, also when take B and the K and the N. B equal 1. Also when take N equal 4, K equal 3. So N equal 4 because the relation M equal M 2K minus 1. B takes this formula 1 and 2. So we take P equal 1. So as a solution, polynomial solution of order 4, U and V, auxiliary equation, P equal 1, polynomial of order 3. Both 5, 2, 5, 6 in these equations. In this equation 4, 2, we find two groups of equation. We must specify equal 0. Depend on you see some parameters of Labium or parameter of Xi, parameter of alpha, parameter of alpha beta, or alpha function of t or beta function of t. Also a parameter A, A4, A2, A1 depend on the type of techniques of solution. There are many or some of conditions. There are many types of conditions specify to group equal 0. Also some parameter condition and some parameter free. From the equation 7.2 this parameter. Also we can solve, we can find solution of auxiliary equation. So before depend on condition parameter and phi xi, we can find the solution of solution is U capital Xit. When both xi return to the first formula of x depend of x, y, t. That is that shows the solution of equation 8.2. I will take some parameter free, some parameter condition, some parameter free. We take some parameter as a function of t, and some parameter also constant. We can show a linear wave as shape as a accordion. As it u as in this 3 dimension, the u x and the t for fixed value of y. Also, this is against 3 dimension for solution for fixed value of x. So use 3 dimension xt, this 3 dimension yt. Another type when took b equal t, b take 1 and 2. When b depend on b, k, and n. b equal 2 and k equal 2 and n equal 2, because n equal m 2k minus 1, the formula of polynomial solution order 2, auxiliary equation also order 2, from equation 9 and 10 to 40, equation 40, we find the two groups of equation must satisfy equal 0, some parameter condition, some parameter free, we can find the solution of auxiliary equations, and also we can find the general solution of equation 4.2. There is some condition of parameter, also some parameter free, we can find the solution of phi, and also we can find the solution u capital Xi, and both finally Xi x to x and y to be the solution of u x y t. For taking some parameter free as a arbitrary function of t, also some parameter is constant, we can show the periodic coming and outcoming and incoming and outcoming periodic wave similarity for x, this as for xt 3 dimension, and the contour plot for u for fixed value of y show incoming and outcoming similarity wave at x equal 0 or similarity at origin space. At the same value, but 3-dimensional the contour plot against y and t for also show a progressive wave with a barrier at y equal line y equal 0. So as a more progressive wave with a barrier of at y equal 0. Also, we can find the rational solutions. This is a simple solution with rational solution. We take p equal p is depend on b and the k and the n. B equal 2, n equal r, and the k equal 1. We can find the rational solution, say rational formula for u, rational formula of v, auxiliary equation k equal 1. So take this formula, and the b also equal 2. So we can find this from equation 13, 40 to equation 42. We find the two groups of solution must satisfy equal 0. So we can solve auxiliary equations. This formula, finally, we can find the solution of nonlinear wave of nonlinear partial differential equation. Solution is rational formula p xi t, and xi t. Finally, we put xi in the similarity transformation to give the solution of against u x y t. This is the first example. Also, the second example speak about 3 + 1 dimension for YTSF equation in space and the time dependent. Also, extended unified Mason can create for nonlinear partial differential equation with space-time dependent. The coefficient in the space-time, space in z and t, the 3-dimension x, y, z, and t. Also, first we omit this term by take uz equal vx. So this equation 1,4 become equation 2,3 nonlinear partial differential equation with space-time dependent. In physics in general, called in partial differential equation in homogeneous media or heterogeneous media, because the coefficient is variable and the variable random. By take this transformation also, I take the transformation 3-dimension to be 2 + 1 dimension x, y, z plus t to be xi z plus t, because xi is transformation alpha x beta y z equals z t equals z, to transformation from 3-dimension 3 + 1 dimension to 2 + 1 dimension. So equation 2,3 becomes this formula in a linear partial differential equation with space-time dependent 2 + 1 dimension. Also, first you will get the relation between n and k in a linear term and the high derivative to be relation between n and k. Here also, n we in general take n equal m relation also the same previous equation, 2k plus 1. The first we take p equal 1, b the power of auxiliary equation, b and the k and the n, b equal 1, k equal 2, then from this relation n equal 2 is we assume solution, take the formula polynomial solution, 2 plus 1 dimension, u and v. Here take another formula of auxiliary equation. So choose a difference between phi xi because the depend on xi zt, the phi xi, derivative xi, derivative z, derivative t, as the same formula but simple different to can calculate because this system is not simplified for calculation of equation. So we take the simple formula different between three auxiliary equation. From equation 5 and 6, both and these equations. For 3, also we get two groups of solution. Must we work to equal 0, the b equal 0 by to give some conditions of parameter like a parameter of space-time dependent, also some parameter of xi, some parameter of nonlinear partial differential equation, nonlinear term on dispersion, some parameter of relation between xi and x and t. Here we add some condition because the parameter not depend on one variable, depend in two variables. So after we satisfy equation equal 0, take into consideration the compatibility. So if you find partial t equal and the partial z equal, so must the compatibility between, but it's because it's the same a z t equal a t z. Also b the parameter of b derivative equal z, also parameter b t z equal minus b a z t equal 0, the compatibility between derivative. Also by some calculation we find some parameter condition, some parameter free. We also find the solution of auxiliary equation from condition, and from solution of auxiliary equation can find the formula of solution of nonlinear partial differential equation. Take u capital xi z t, and finally we put xi alpha x z beta y to find the u x by t here, and I write u and v, so I plot nonlinear wave configuration for u and v. By take some parameter of free parameter of solution u and v, we can find this is show 3-dimension z and t, space for z and the time t for u for fixed value of x and y. By take some parameter as arbitrary function of z and t to show cylindrical soliton, like a cylindrical soliton for 3-dimension and contour plot. For u, for v, the difference of which for the same value at upper and lower called semi-cylindrical soliton for upper and lower. This is 3-dimension and contour plot for the same solution of equation 383. For more valuable another value, we can find the 3-dimension the solution as like show a molar soliton for u and the contour plot for 3-dimension and the contour plot for solution of equation 83. This also that the same value can show for solution of equation 2-3 for the same value previous, show the molar soliton with a guarded along space z, dimension z. Also another solution, when take previous solution, take p equal 1, here take p equal 2. Depend the method depend on two value b and K order of auxiliary equation of order of polynomial solution B equal to, so the formula of auxiliary equation phi derivative xi phi derivative z also phi derivative t. So solution is elliptic wave solution or elliptic solution depend on the values is calculated from table depending on C4, C2, C not. Also I take one formula. So also this is U as polynomial solution of order 2. Also, we take in consideration compatibility when I calculate, we must compatibility between variable of solutions A and B, also variable of a linear partial differential equation. I take C4, when take C4 equal minus M, M is not the modulus of the Jacobian elliptic function. C2, C naught is the standard formula. We can find the solution of the elliptic solutions. Standard formula from table of reference 20. We find also from value of xi some and some condition parameter. Finally, we find the solution of nonlinear partial differential equation U capital Xi ZT, and finally we put xi equal alpha x plus beta y to find the solution of nonlinear partial differential U against 3 plus 1 dimension x y z. So we can plot this equation 13. This is plot of 3 dimension and 2 dimension for U against space z and time t. Also for take arbitrary parameter, free arbitrary parameter for space and the time, depend on the space and the time, and it show a capillary wave around original 3 dimension and contour plot for U. Solution of equation 15. Also the same value we can show the 3 dimension and contour plot for sorry, it is V, not U. It's V against Z and T. It show it upper and lower progressive wave. Also, we can find the rational solutions depend on three numbers B, N, and K. P equal 2, N equal R, K equal 2. We can find this formula of auxiliary equation B1 and K2. Also the rational equation N equal R equal 1. So from equation 14, 15, we can we both in the nonlinear 2 plus 1 nonlinear partial differential equation. Also we have two group of equations as phi equal 0. We take into consideration compatibility between each parameter. Find under this condition, we can find the solution of auxiliary equation, and finally we can find the solution of nonlinear partial differential equation dependent on some parameter and some parameter condition, some parameter free. Take as arbitrary to show the nonlinear, how to find the nonlinear wave from the solution. Also, this illustrates the solution of equation 83 for some parameter taken as free or some parameter constant parameter, a value of x, a value of z and t, show 3 dimension and the contour plot to show the lattice wave was tunneling around the original. This reference. Yes.
So why was P always an integral?
P?
Yeah.
this value.
Yeah.
B. Because it's B's number. I take at
Why is it an integer? Why not P is a half?
the solution of this model depend on this equation. This is the main equation. I can
understand
take
that.
it to can
That's not
integrate.
my question.
Yes, to can integrate that.
Why-
Maybe
Why
take
can't P be a half?
B half. B B equal 1 and this method techniques if B equal 1 or 2 as higher that we can solve this equation to find a solution the solution of this equation or of this integral equation. Yes, B take two. Yes, B.
Or 3 or 17. I mean, why are you only picking P as 1 and P as 2? That's my question.
Because if I have this, I calculate the coefficient of 5. So much 5 is equal what is constant equal 1 equal 2 equal 3. So I can't if I can't halve I can't coefficient for 5.
So you can.
You can't by techniques of
So
this
you can
method.
or you cannot?
I cannot.
Why?
I cannot because depend the coefficient of phi. Coefficient of phi is maybe coefficient of phi 1, phi 2, phi power 1, phi power 2, phi power 3. It's dependent this
So there's
formula.
there's no balance.
This method I think it is common for because phi is arbitrary. You can find the elliptic solution, can find the solid solution, but not treatment with initial conditions.
That's not my question. You're sort of wandering
not
off.
initial
Maybe
with
we can talk
can discuss.
I don't think you understand my question. That's okay. We'll see if anyone else.
Yes, I understand why you use B equal 1 and 2 only.
Yeah.
Yes, yes,
I didn't hear the answer.
yes, because techniques of this solution depend on the order of phi. I take the formula to can solve it. First, second,
They might be interesting for some applications.
numerical. This is an analytical solution. All analytical solution. I can't use numerically. I can't use boundary condition. Also, we must this equation be integral. Also, techniques depend on this polynomial power of power coefficient must be okay.
So okay, I don't want to take up the time.
Okay.
We can discuss privately.
Yes.
Is there any other? I don't want to dominate the question.
Let's say 15 minutes. And then if you have questions, feel free to ask.
I understand your question. I put the equation in you to find power of phi. Mass power phi is positive. So coefficient list of phi. If a coefficient list of 3 power 3 over
It's how it's kind of like informing. What it looks like, what you looks like. The exact solution is not important. No, I don't think that's important. Not approximate, I mean, it's well defined by differential. Yes, need an explicit formula for just need to be able to understand the behavior. Can you send me the slides or if you have a paper? It's very interesting. It's 100.
Are you the next speaker? Yes. Are you the next speaker? Could you please, please come?
Sorry, before we start, here's our, oh no, online, don't need to get. Here's the venue for the conference dinner tonight. I know some of you are driving, someone yes. Here's the venue for tonight. We're gonna start at 6 p.m. So you can take the venue down and then.
Another quick announcement, tomorrow at 3 o'clock, Professor Meleshko will give a talk in the mathematics department on campus. We will take all the participants there after lunch. And then after his talk, there will be a tutorial session for students with Professor Meleshko. So students and supervisors, please keep in mind, there will be a tutorial session tomorrow from 4 to 6. And then we will conclude with a dinner for everybody who is at the tutorial session. Thank you.
Okay, our next speaker now is Professor Jamal. So we are starting at 11:15. So we have 30 minutes and then we can continue from there.
Thank you everyone. Firstly, I'd like to thank the organizers for all the hard work, Prof. Boyle, Prof. Tara, for putting together this lovely event. I always look forward to escaping Joburg.
So you know, when we were trying to organize in Johannesburg, I was told, don't.
Well, you know, I suggested Sun City, which is not far, but I think we don't have money for that. So maybe someday someone has deep pockets. Please contact some of the organizers. So I'd also like to thank the Center of Excellence, who has supported the transport and the travel costs, or the travel costs for my students to attend this conference. So I'll be speaking about some classical partial differential equations. Just a brief outline, a brief mention about recursion operators, and we'll see that the equations that we are studying, they form a hierarchy that contain differential they contain a recursion operator. And this talk also includes the double reduction theory that was mentioned, I think, many times now. And we actually were not aware of the multiple double reduction theory. So it would be interesting to even see if it can be applied in this case as well. Maybe that's some future work. There are two cases that appear in this case study. Normally, I would spend a good 10 minutes defining a symmetry, explaining some theory and so on. But I take it for granted that everyone here is quite proficient with the method. So I've removed all of that from the talk. So this recursion operator, for those of you who are not aware, this is basically when you have an integral differential operator, which maps a generalized symmetry to a nonlinear PDE to a new symmetry. And this revolutionary work was done by Over in 1977. And this paper, it sparked off many other avenues of research. This idea of the recursion operator was, I think, first seen by Leonard, someone called Leonard, before that, and Olver took that on and really developed the theory further. So as was expected in this paper, the benchmark equation was the KDB equation that was studied under this theory, and it was shown that you can write it, you can generalize the equation with a recursion operator to generalize the flows or symmetries that are higher order. And basically, when you have a recursion operator, it is thought that the PDE has infinitely many higher order symmetries. And this is one of the features for complete integrability. In 1987, by Focus, he said that an equation is completely integrable if and only if it contains infinitely many generalized symmetries. So they are, this is just a recent interest of mine. I haven't been able to really delve too deeply into this topic, but basically there is also a symbolic software package in Mathematica, possibly in Reducer as well, but I think mainly in Mathematica, by Baldwin and Herman, that allows you to construct recursion operators. They use some sort of a weighting to come up with how to calculate these integral differential operators for a PDE. Herman obviously is well known from his work on the homotopy operators, especially with multipliers. So I should mention that this is work that I did with one of my former students since graduated. And we looked at Berger's hierarchy, right? So this is the nonlinear PDE. And you can see that it contains these differential operators, the X. And basically N here are the integers running from 1 onwards. And basically when N is 1, you get the infamous Berger's equation, which is given by equation 2. Now, you notice that this hierarchy is of order n plus 1 in derivative. It is well known that Berger's equation can be linearized by the Kohl-Hopf transformation, which was derived or proposed in 1950. So the idea that we were looking at is, are we able to solve the full hierarchy for all n? And obviously, working in the field of symmetries and conservation laws, those are our tools. Symmetries didn't initially feature because actually this is easier to do from the point of view of a double reduction. We'll see why shortly. So, I mean, Berger's equation has many physical applications. For example, traffic flow, gas dynamics, etc. And if you look at the case n equals to 2, then we get the STO equation, given by equation 3. And this also is shown to have many physical applications, for example, in quantum field theory and so on. So you can see that the equation is getting in the hierarchy of the PDE. As n increases, we are getting more nonlinear. So as just an example, here's the PDEs for n equals to 3 and 4. You have the nonlinearity and the complexity of the equation increasing. And so we thought, you know, is it possible to try and solve again for all n? I'm not sure about applications of these equations. I'm not sure if anyone has looked at the higher order members, but possibly some extensions can be made from the other lower order cases. So if one looks at Berger's equation, case n equals to 1, so we have these 4 symmetries, right? Standard 3-point symmetries. And if you looked at the STO equation, which is n equals to 2, we get only 3 symmetries. X1 and X2 are obviously the time translation and space translation symmetry, right? It's easy to see that if we looked at higher n or for arbitrary n, then both beyond n equals to 1, then you would get the 3 symmetries x1, x2, xn, right? The last one there obviously dependent on n. So as I mentioned, we want to look at this from the point of view of a double reduction. So we need the conservation law for the full hierarchy, or at least one conservation law for the full hierarchy. Actually, you could have worked this out by just looking at the equation, because it's almost written in a potential form. So this is a conserved vector for the full hierarchy. That's easily proved, right? I'm sure there are other conservation laws. We actually didn't look at the multipliers or anything like that. Well, perhaps or not. Maybe it'd be interesting to see if we could generalize the results for other n. But this one is an obvious conserved vector. So typically, Tt would be the conserved density, and Tx here is the conserved flux, which obviously is dependent on the n, and you could generalize then, or you could generate the conserved fluxes for all n. It's the density that doesn't change, right, for every n. And for the flux, for example, you have n equals 1, you have the conserved density 9, and so on. So these are easier to deal with than the equation itself, right? These conserved vectors, which is why we looked at the double reduction. So as we've seen already, but I'll remind everyone, the association between symmetries and conserved vectors, this was done in the year 2000 by Kara and Mohammed. I think that's Kara's most cited paper, if I'm not mistaken. So this is the condition equation 13 that gives you the association condition between your symmetry and conserved vector. If it's satisfied, you know there's an association, and you can proceed with the double reduction. It's obvious that x1 and x2, the scaling and time translation, are associated with the conserved vector that I put up for the nth, the nth conserved vector for the hierarchy. The case xn was dealt with separately, so I've omitted it here, but we'll focus on just the simple case. So what does the fundamental theorem of double reduction say? Basically that you can reduce the conserved vector by change of variables, let's say r. And so your conserved vector, it was tt and tx, but now you change into a new variable, tr. And essentially tr is given by equation 15. And this was from Schoberg's paper. This was generalized, I think, by Papara and his collaborators sometime later, generalized for, I think, more variables, was it? So anyway, we have this formula for calculating TR, and R and S are these similarity variables that come from the associated symmetry X. So basically, we then use this idea to transform the conserved vector. We have this new variable U tilde. So we just use the associated symmetry, a linear combination between them. And so we have these new variables, R, S, and U tilde. And so you calculate the TR based on Schoberg's formula. And so you get, it is a reduced version, right? The reduced conservation law. And obviously it's still too complicated to deal with at this stage. It doesn't let you go anywhere at this point. But we know that based on the fact that TR is a conserved quantity now, then the total divergence will be 0. So if you integrate both sides of 19, you basically get this equation here, TR equals to K, which you would then try and solve. And there are two obvious cases that jumped out at us when solving TR equals to K. So if you look at the first one is when K is 0, that's quite a simple case, and when it's not 0. So actually the Hofkohl transformation is what inspired this other transformation, and actually it works for the full hierarchy, not just for the case n equals to 1. So we applied this this transformation, C V prime over V. V prime then, V satisfies equation 22. And so this is now linear in derivatives, basically. And this is an ODE hierarchy. So we went from a PDE hierarchy that was nonlinear into an ODE hierarchy that we can study. This transformation was used in both cases, but I think I've only shown it for the one. So we can easily solve equation 22 using any standard calculus-based methods. Basically, you can find linear factors for such an equation. And we prove this. Basically, we proved that the bottom part is V, basically. And this is just CV prime on the top there with some manipulation. And so you can get a solution for the Burger's hierarchy by simply reversing the transformations. I just briefly outlined the proof. You can, as I said, it has the roots of 0 as one of them, and the other roots there, set of roots there. And so you get V, and then simply reverse the transformation. If you have roots that are complex conjugates, easy to manipulate, you just apply what they teach you in undergrad, Euler's formula, and you manipulate the constants to ensure that you get a real solution. So here's a very simple illustration. If we take for n equals to 1, And obviously you could go higher n. With this formula, it's quite straightforward. You would get the reduced conservation law in 25. Apply the lemma that I put up, you get the ODE for this case. And basically solve. You can solve this for the roots. You can get this solution alpha v. Reverse the transformations and you have eventually the solution for the original PDE, which in this case is Berger's equation. So this was the case k equals 0, which is quite straightforward. When it came to k not 0, this wasn't as easy to find a solution, an analytical solution. Basically, we looked at the symmetries then. We looked at the symmetries of this case, and that helped us go forward toward the solution. So we had that when you have n equals to 1, then you have these 8-dimensional Lie algebra symmetries, right? You can see the symmetries are quite strange looking because of all the square roots and so on. Not the easiest ones to look at or to work with. But generally, as we iterated the results, we found that we could find the symmetries for n greater than or equal to 2, right? And they were of a certain type, so you had XR, XV, right? And the number of symmetries are n plus 3. So the n plus 1 symmetries we denote by xin. And these are just the symmetries here, it's e to some power, which is a root, basically. I here sums to n plus 1. And we found that this Zin is given by the n plus 1 roots of this polynomial. I attended a talk recently at Ames where Peter Clarkson gave a talk online, and he had some interesting, if you've ever seen his work on roots, and he comes up with these lattice diagrams that have some geometric significance, and he tries to find patterns in all of these roots or roots of polynomials. We did not attempt that, but we did look at finding the roots of this polynomial. So we found that Maple can only handle the root finding for low n, so low values of n. But Mathematica, on the other hand, was extremely powerful in finding these roots and could actually generate roots for extremely high n. So finding the roots was quite simple because once you have the roots, you know the symmetry, right? So we can write down the bracket relations for these symmetries. And what we also realized is that remember this was for n greater than or equal to 2. But for the n equals to 1 case, which was 8-dimensional, we have that some of the symmetries do come from the same polynomial, but not the others. So for example, if you had this polynomial, for the case n equals to 1, you have these roots that do give you the symmetries. It's unclear where the other symmetries come from. Certainly not from this polynomial. So as I mentioned, we were just playing around with the roots. And obviously some of the roots are these complex conjugates, right? So unfortunately, well, there's nothing interesting to be derived here. But as far as we can see, these polynomial roots are not our area of expertise. But basically, we're just testing the ability to generate the roots for Mathematica. And actually it went up to 23. When n is 23, it went up quite easily to handle the computation. As soon as you go over 23, The Mathematica seemed to slow down a bit, but was still able to eventually give solutions. This is also for, we have to set C and K as some value, but you could choose any C and K. It is not necessary to really specify. This is also the standard for the K equals 0 case, the roots over here. This is not surprising at all. And so basically, once you have the symmetries now, you have the symmetries for the full hierarchy, the ODE hierarchy, that is, for the case K not 0, then you can use the invariant method to write down a solution for V. We chose one of those, we chose that symmetry, seems to be the obvious case. And so you can write down the solution for V. And obviously, if you know the roots, then this is easy to integrate. And once you know V, you reverse the transformations, right? And you're able to find, remember, you will see V prime over V. And essentially, you would find the solution for U. And you could use this to generate the solution for the full hierarchy, given that you can compute the roots of this polynomial. The roots were actually huge. They went over at least 2 pages. Each set of roots went over 2 pages. So they were hideous to present. I've omitted that. And obviously, once you put the roots, use the roots to find V, the solution for V is also very lengthy and cumbersome. And obviously then for U as well. So here's just some graphical analysis there. For example, when N is 1, we did set some parameters here, and we did get curves that appear like this. When we look at N equals to 2, these seem to be more interesting. I'm trying to remember what we set as our parameters. I think it was C1. It was C, various parameters, if I recall correctly. I'm not sure what they are. Sorry about that. So these are solutions for V. And then you can, from there, look at solutions for your U. So this was the N equals to 1 case, corresponding case in 3D. And N equals to 2. So they look like these wave-like solutions, which is, well, the underlying transformation was wave-like. So it's to be expected. It would be interesting to see if we could do some sort of a multiple reduction and maybe find more conserved vectors for this equation, if it's possible. We haven't actually looked at the multipliers at all for this equation for any, and obviously you have to generalize it to the full hierarchy. It would be nice to have students to do that. The problem I've been having lately is that all my students, they tend to get jobs. But they get jobs. I mean, it's indicative of the economic problem in South Africa. So you want to have independence, you want money. You've been studying for so long. So they actually get into jobs. And then they have to juggle between research and their jobs. I'm just wrapped up. So yes, this is the problem I'm facing. Here's some references. I'd also like to mention, I'm currently guest editing a special issue in the journal Practical and Fractional. It's actually the 2nd edition. The 1st edition went quite well. If you can afford the APC, you're welcome to submit. What is this? It's over 2,000 francs. So I think in South African rand, it's over 40,000 rand.
Wow.
Probably. So, well, obviously in this area, I focused on symmetries of the fractional differential equation. So that's my angle. But anyway, thank you for your attention.
Okay. Thanks, Prof. Any questions? We've got about 4 minutes for questions.
First, a comment. So in a couple of talks, we've seen this condition for association of a symmetry with the conservation law. It's overly restrictive because it doesn't take into account that a symmetry can move a conservation law to a trivial conservation law. So yes, the paper may be well cited, but it's not the best reference to cite because it's overly restrictive. So the correct formulation is in a later paper of mine with Kara and also in the new work on multi-reduction. So please use the proper formulation of association and not this overly restrictive one, because you're potentially throwing away things. The second comment is the literature has a lot of knowledge about the Burgers hierarchy. So what you were doing is finding a particular class of similarity solutions. But in fact, you can do much, much better than that because so the original Burgers equation, as you pointed out, is linearizable by Cole-Hopf. Likewise, all the higher equations are linearizable, so they can be reduced to linear PDEs, which can be solved, for example, explicitly by Fourier transform. So, I mean, you can do a lot better than just this limited class of similarity solutions. If your goal is to find exact solutions, you can write down a general formula for the general solution of each member of your Burgers hierarchy. So there's if you're knowledgeable about the literature, there's a lot more that can be done with this than what you're doing.
Right. I suppose you gotta know when to hold back and cut off. But yeah, it's good to be exhausted. I think you've said that to me before in another platform.
Because why find just similarity solutions when you can find the general solution of the hierarchy?
Sure.
Okay, so thank you.
Okay, just 1 minute. I'm going to take one because we are running short of time, unfortunately.
Hi, thank you very much for your talk.
Thank you.
So I don't study differential equations. I'm a number theorist, but some of the things I study is linear recurrent sequence where every member of the sequence is a linear combination of the previous, let's say, k of them. And there you have a characteristic polynomial, like in differential equations, you have to find the roots and so on. So for example, those things that you showed there, if you take c equal k equal to 1, they become like x to the n minus x minus 1. When n equal to 2, it becomes the characteristic polynomial for the Fibonacci sequence. And then you can ask what happens when n goes to infinity. Then what you can prove that those images that you have there, they appear, and we proved it in some papers. We proved that those roots, for example, they all tend to 1 in absolute value, and they are uniformly distributed around the unit circle, exactly as it appears in your picture. So I think this one, you can do it for every fixed c and k. Once you send n to infinity, then your roots are going to have absolute value around 1 over c. And then they are going to cluster around like that. And they are going to be uniformly distributed. And those things, you can prove them. So you can prove that the images that you see there, actually they hold for fixed c and k and then going to infinity. So that's all.
Thank you. That's great.
Okay, once again, thank you very much. Those that still have questions, they can catch with her during lunch. Okay, thank you. So our next speaker is Dr. Matthew. Dr. Matthew.
Yes. Good day, everyone. I'm Matthew Ibinu, and I'll be talking on the topic titled Approximate Analytical Solutions of Linear and Nonlinear Differential Equations and Applications. Here today is only one presenter, but two authors. So in time of questions, the two authors will be responding. For the presentation, there will be introduction, then what is contribution to knowledge, the preliminary, and then the main results. To start with, as an introduction, it is common knowledge that using mathematical modeling, one can test the hypothesis, and also through that we can confirm the experimental results, and by mathematical modeling as well, it is possible to simulate the dynamics of complex systems. And by using mathematical modeling, it can be biological creations can be easily considered, and there a lot of time can be saved while using mathematical modeling and also on complex systems. And through the mathematical modeling, one can understand the basis of dynamical systems. However, we know that mathematical modeling leads to it often leads to integral and differential equations. The challenge is that exact solution of some integral and differential equations are difficult to obtain, and that is to get their using analytical method or to get their exact solution in most cases are difficult to obtain, and therefore the approximate or numerical solution, that is why it is trendy this day. Now solving differential equations, there are many numerical and approximate methods that have been considered for solving differential equations, which include spectral method, artificial neural network, operation matrix technique, collocation method, iterative Laplace transform method, irrational iteration algorithm, finite difference method, homotopy analysis, homotopy pade, homotopy perturbations, irrational principles, and Sumudru or hybrid of Sumudru transform. These are some of the methods that have been developed, some skills that have been developed for finding the solution of differential and integral equations. Now, with all these methods, what is known that most of these methods that have been listed are not each free due to one, some of them have their association with certain impediments, and some, the result that they produce are divergent. And there are some also that before you can apply them or before you can use them, there are some unrealistic assumptions which have to be made. And some involves the calculation of Adomia polynomials. And some also, in using them, we have to undergo a lot of lengthy calculations before we can arrive at the reasonable or acceptable results. And some also have the limited convergence and no compatibility with when we look at the result that some of the methods that they yield, they are not compatible with the physical system, non-linearity of the physical system. And therefore, for this study, I want to present an integral method and its average. And this method, that is, these two methods, they are suitable for solving differential equations of integer and non-integer orders. And now the result, that is present efficient method. These methods are efficient
with few computation steps and they produce exact solutions. And at the end, we apply this method, that is, we consider application in nuclear physics by one, introducing models with non-integer order derivative for a decay process, and also obtain and compare the solutions of the model that is given by integer order with the one given by non-integer order. And we also try to modify the model, that is the decay process. We also try to introduce the delay into the decay process. To start with, as what we are, the presentation is based on Sumudru transform. Let's quickly review the Sumudru transform. The Sumudru transform for a given function y of t is defined by equation 3.1 for t greater than or equal to 0 and for y of t in lambda, where lambda is defined by that. Where is that the definition of the lambda? Is the set of functions. And this Sumudru transform is an integral transform, just like the well-known Laplace transform. And this is the definition of the Laplace transform. To compare the Sumudru and Laplace, you can see that there are a lot of similarities between the two. And we can just talk about that. If we denote the Sumudru transform by y of u and we denote the Laplace transform by lu, we can talk about, we obtain this similarity, we obtain this duality relation between them. That is, for y of s, which is for Sumudru, the duality relation of it to Laplace is s L of s. And for Sumudru, for L of 1 over u, for Laplace, L of 1 over u, the Sumudru translation of it is simply y of u. So that gives the duality relation between the Sumudru transform and Laplace transform. And this Sumudru transform, why it is, well, what we know about it is that it preserves units and it is very efficient in transforming linear differential equations to algebraic equations that can be easily solved. And also using Sumudru transform is interesting or is appealing because of its easy visualization and efficiency in obtaining the Lagrange multipliers. Whenever it is applied, it makes it easier to obtain the Lagrange multipliers, which will be demonstrated shortly. And another thing is that this Sumudru transform is satisfied the linear property. We are all aware of linear property, that is Laplace Sumudru transform satisfies it. So throughout this presentation, we are going to use the common notation for the set of real numbers as well as the natural numbers. That R and that N will denote that of real and real and natural numbers respectively. And this gives so this table gives the Sumudru transform of some selected functions. When you are given function to be y, for y of t, when it is 1, that is what the Sumudru transform of 1 is 1, and for t is u. And for t to the power n over gamma of n plus 1, as it is known that gamma of n plus 1 is n factorial, the Sumudru transform is simply e to the power n. And for e to the power 80, the Sumudru transform is 1 over 1 minus u. And similarly for others. So these are the Sumudru transform for some selected functions. Now the Sumudru transform for the first order derivative is given by 3.0. And for nth order derivatives, the smooth transform is given as 3.4. Given two real numbers A and B greater than positive real number A and B, where and alpha between 0 and 1, the capital fractional derivative of order alpha is defined as what is written on the board. And the smooth transform for this is given by this equation, that is when A is equal to 0. That is the smooth transform for capital fractional derivatives of order alpha. And also capital Fabrizio fractional derivatives in the capital sense, which will be denoted by CFC of order alpha, is defined as this, where mu is equal to alpha over 1 minus alpha. And the smooth transform for CFC of order alpha is given as this. And also we need the definition also. The ABC, which we denote the smooth transform for ABC of order alpha is given as this. And the smooth transform for it also is also given as this. And the conclusion product of phi and psi is given as this. And you have the smooth transform also for the convolution product to be u of phi of u and or to be as given as written on the board. Now, the Mittag-Leffler function E alpha of t is defined as this. And we have the following result on the smooth transform of Mittag-Leffler functions. We have these two results, which we shall need make use of during the course of the presentation. Now, the decay process of order 135 is given by, that is the ODE, that is given by this ODE. And these are the symbols, that is I represent the number of iodine number, and we have the O to represent the decay constant. And gamma is also a constant, which is the product of some parameters. This is the model that we want to study. This model is represent the decay of iodine 135. Now, for this model, this study considered this. We now want to introduce this analog. This is the analog of the ODE for the decay process of the iodine. This analog now that is being introduced is given with fractional derivative. The one given before is ODE, but we want to study this analog of it, which is given by the fractional derivative. And this study will consider this. This study consider using this will be studied using the method, that is the smooth transform, to obtain the solution of this equation 1.2 when it is given by capital fractional derivative, CFC, and ABC. We want to study this, the solution of this model, which is given by the fractional derivative when the fractional derivatives are given by this. And in addition to that, we want to consider that if we introduce the delay into this model, then and still study its solution as well. Now consider, that is the first one now, given by, we want to study by the model given by the capital fractional derivative. This is the nature of it. And in order to solve this one, we want to apply the smooth transform method. To apply the smooth transform method, the first step is to take the smooth transform of that given equation. And this is how to take the smooth transform. And it's given as this, and the smooth transform will lead to this by the property of the smooth transform. And this can be simplified to obtain this. And the next step is apply the inverse smooth transform and using the results, a given result on Mittag regular function, which state as this. If we apply this result, then we obtain this solution for this, we obtain this solution for the model that is given by the capital partial derivative. If we look at this solution, we can compare with the solution for the ODE, which is given by 4.4. You can see the similarity between them. That is, using the smooth transform method, we are able to, we introduce the model given by the partial derivative. First of all, the one given by the capital partial derivative. And we use smooth transform to obtain the solution, which is given by 4.3. And this is compared with the solution of the model given by the ODE, which is 1.4. The similarities, you can see it between them. Then we move further to consider when the model is given by the capital Fabrizio functional derivative in the capital sense, which will be this. In order to solve this one also, we apply the smooth transform method by taking the smooth transform like in this form, then it leads to this. This also can be simplified to obtain this. And the next is to apply this result also, which has been stated before. Applying this result and taking the inverse smooth transform, the solution is also obtained for the model given by CFC to be this. We went further to consider the model given by the ABC, that is in the capital sense, which is this similar procedure in order to apply the smooth transform method. Then we take the smooth transform as shown on the board, and this leads to this. And then it's simplified to obtain this. Applying again now this result on the regular functions, and applying this result and taking the inverse smooth transform, the solution is obtained to be this. Now, the next is that is how to apply the smooth transform method. Now, the next thing is to talk about the hybrid smooth transform, that is a hybrid of smooth transform, which will be called hybrid smooth operation method. So, hybrid smooth operation method is a hybrid of smooth transform with a operational iteration method. And what is known is that if you look at most of the occurrences, most of the systems, that is delay associated with most of the systems. We know that it's just like the natural component of most of the systems. And in general, dynamical system with delay, they often defy the well-known analytical methods for obtaining their solutions. So this method called the hybrid smooth operational method, which is a hybrid of smooth transform. We want to consider how to use it. We want to consider its application to the models, to the model that involve the delay. That is, we want to consider its application because it is an efficient method in obtaining the approximate analytical solution of delay differential equations. So this method, from what you have studied, it also leads to exact solutions of most dynamical systems. And so this study will present HSP method for the delay differential equation that are given by the capital sense, that are given by the capital functional derivative. The hybrid smooth operational method, given a nonlinear system, and this is how to, that is the hybrid smooth operational system, just go like this. Given a system of this form, which involves a delay, where in this place, the lambda is a delay. You see, and tau, that is lambda. Sorry for mix up. Tau is not involved. Is the lambda is introduced, the delay is introduced in form of Pantograph differential equations. The lambda there is, that is, we have it to be y of lambda t. So phi is the nonlinear operator and psi is phi is linear operator and psi is not linear operator, and g of t is a given function. What we observe is that equation 4.5 is a nonlinear equation and it is associated with the delay. That y of lambda t, the lambda there is the delay, which is in form of the Pantograph differential equation. So it is a fractional derivative also. It is a model associated with fractional derivative. So to solve this equation, the Smoot transform, that is, take the Smoot transform in this form, and then it gives this. And the next is that from this one, then the formula will now be introduced. That is, Aldrich Smoot operational formula is now obtained as this, as 4.8. The next thing is that how one need to determine the Lagrange multiplier, which is phi of u, by taking its classical equation operator and considering the Smoot transform of y of t minus that one as illustrated, then the Lagrange multiplier is obtained as to be u to the power minus alpha. Then when we substitute that one back and we take the inverse Smoot transform of the previous equation, then we obtain the iteration to be this. That is how to apply the Smoot arbitration method. Why in this place one of t is equal to y naught. So what we now did is that one is just to introduce what we mean by the Aldrich Smoot operational method. Now this method, before we applied it with the model that we are considering, first of all, we verify its efficiency. How efficient is the method? In order to do that one, we apply it to a model whose solution is already known. You call that this model has already been solved by using the Smoot transform method. So we apply the Aldrich Smoot transform method now. That is the hybrid of Smoot transform. It's applied to this model to see what we are going to get in order to determine the efficiency of the Aldrich Smoot transform method, which is being discussed in this presentation. And when it was applied, what we observe is that it yields a exact solution at the Smoot transform. That shows the potency of the Aldrich Smoot transform method. That is, it is very efficient in obtaining the exact solution when the delay is not involved. That proves the potency of the Aldrich Smoot transform, which is denoted as HSF. Now the model for the decay. Now the model for the decay of this one is given by this record that the model with the ordinary differential equation, with the integer order, is given as this. And what we have done so far is that one, we introduce we consider the analog of this model, which is given by 4.11. When the partial derivative is given by capital partial derivative is given by CFC and is given by this, and we have studied the solutions of this one using the Smoot transform method. So and obtain the solution. Now obtain the solution of this model, that is 4.11, by the Smoot transform method and hybrid of Smoot transform method. What we now want to consider is the last thing is that we introduce the delay into that system, into that model. We know that the presence of delay in mathematical models can improve their adequacy in the description of the system under consideration. And therefore, this study we introduce the delay in this form, where lambda is greater than 0. And this equation 4.5 is a typical pantograph type equation with fractional order derivative. So this study consider when the fractional derivative is given by Again, also, that is for this one, when the day is involved, we also consider other day theory cases. And what you obtain is that it's also that using the smooth transform method give the exact solution this for this one. That is when the delay is not involved. Use smooth transform and hybrid of smooth transform. They give that exact solution for the ordinary differential equation that for the model given by the integer order. And for taking the parameter to be this, we obtain this graph. And also, we also observe that this exact solution is also obtained for this one, that is the one with the fractional order now. For this one, this exact solution is obtained. That is the two methods. They use the same solution, which is exact solution for this model. And taking the parameters to be this, we obtain the graph of this one also to be this. And lastly, this model 4.15, because this one involves delay, the smooth transform cannot work for it. Therefore, we apply the hybrid of smooth transform and we obtain the solution to be this for it. And for this one also, taking the parameters to be this, we obtain this graph for it. In summary, what we have done there is that smooth transform, in conclusion, smooth transform is a modified form of Laplace transform. And for each property of Laplace transform, the corresponding property can be obtained for the smooth transform. And this study introduced two types of memories into the radioactive model in order to enrich its dynamics. The two types of memory that we introduced are one, fractional derivatives as well as the delay. And we apply the method of smooth transform and its average in order to study their solution. And we observe that smooth transform and hybrid of smooth transform method give accurate result with few computation steps and do not impose restriction on the solutions. Thanks for listening.
Okay, thank you, Matthew. We can only take one question if there's a question. Okay, thank you. Okay, and then our next speaker is Dr. Kumar.
Well, good afternoon, everyone. Myself, Sachin Kumar from the Department of Mathematics, University of Delhi, India. First of all, thank you very much for organize this wonderful and nice international conference on the symmetries of differential equations. Yesterday, the Professor Subisu Maya and the Professor Stephen Janko discussed about the multi-reductions of the symmetries. So today I'll extend the title of the Lie symmetry with the generalized invariant solutions and the dynamical structure pattern of the 2+1 and the 3+ dimensional nonlinear evolution equation. So in this talks, I discussed the introductions, the differential equation application, the generalized BKP. Here I'm taking the one particular generalized BKP Boskin equation, what is the Lie symmetric method and how to apply on this method and finding the group invariant solutions for a analytic solution. So as we are aware of that today, the many researchers finding the analytic solutions of the highly nonlinear partial differential equations, which plays an important role to understand the qualitative and the dynamical behavior of the nonlinear phenomena in the various field of nonlinear dynamics, nonlinear optics, soliton theory, shallow water waves, and the other field of the physics. So basically the analysis of physical models allows the predict and understand the possible behavior of the corresponding physical symmetry. And we know that the Lie symmetric method was introduced by the Sophisticated Lie, and which is the one of the most powerful technique to finding the analytic solutions of the nonlinear PDEs. And we know that the Lie symmetric method is based on the invariance of the PDE. So the application of Lie group of differential equations are mainly established by the Lie and Amen method. And the elementary examples, as we are aware, the translation, rotations, and the scaling. And we know that the differential equation, there are the two types of differential equation. One is the one type of the ordinary differential equation, and the second one is the nonlinear. So these are the basics examples, and we are aware of that under the undergraduate. So why we need to finding the analytic solutions? If we are finding the analytic solutions of the highly nonlinear dynamics, so you can understand the dynamical behavior of the nonlinear phenomena to predict the internal mechanism of the wave, like the shallow water waves, solitons, like solutions. So it's important to finding the analytic solution. So we are taking these types of equations to demonstrate the dynamical of the bubbly waves and their occurrence in the ocean engineering and the ocean physics. So the first of all, there are so many methods to finding the analytic solutions, as these are Lie symmetric method and the Hirota bilinear method, Jacobi elliptical method, generalized conditional symmetry, exponential function method, inverse scattering, hyperbolic, extended tan hyperbolic, and generalized exponential method, and others are to finding the analytic solution. And there are 70% of the world working on these method to finding the analytic solutions. And as we are aware of that, the Lie symmetric method is the very highly powerful tool to finding the analytic solutions. So as our research scholar are also working on by the various analytic approach, and we have modified the some standard generalized method, the modified generalized exponential method, inverse G' expansion method. And these methods are already modified by our research group. So the some popular nonlinear evolution equations, we are taking the some well-known famous equations, the 2+ dimension KP equations. Why it is called 2+1? Because here x and y is 2 and 1 represent is a temporal, the time variable. So, and u is here the dependent variable or a wave function. So these are some standard equations, the 2+1 KP BPM equation, 2+1 D modified KP BBS equation, and 2+ BK equations. So these are the wave type equations, and some others. This one is the 2+1 D variable coefficient. Here, the AT, BT, CT, KT are the variable coefficient with respect to T. Note is the constant coefficients. Other equations are the constant coefficients variable equation. And these are some, we know that, so this is our original equation when we apply on this equation. So the 3+1 dimension generalized BK Gaussian equation. And here, this is the nonlinear terms Vx, Vy. So here, the Vx is the wave amplitude or a wave function along with the 3 spatial coordinates, means x and y and x, y, and z. And t is the temporal coordinates, and these all the derivatives with respect to x, y, z, and t. So why I'm taking to choose applying on this equation, and when I go through the literature, so we have seen that the Deng et al. Constructed the rational form solutions by using the bilinear method. Waswa and L. Antoni is applied the simplified Hirota method and find the 1 and 2 soliton solutions. And as well as the Verma and Thor applied the 20th Spanelli expansion and the Bell polynomial to finding the solitone form solution. So that's by motivated by this work. So I have applied on this equation, the original equation, generalized BKP equations by the Lie symmetric method or a Lie group of transformation method. So as we are aware, okay, these are the basic books, the Lie group and the various terms by the P.J. Oliver, P.J. Blumen and Comay, Blumen and Cole, and one more important book, and the Blumen and Anko, which is the symmetry and the integration method for the differential equations. It is also important to how to learn and how to apply the Lie symmetric method. So this is the base, the Lie symmetric method, how to apply. So to solve the nonlinear PDEs, the Lie symmetric reduce one independent variable. How to apply the Lie symmetric method? Suppose if we have the 3 plus 1, there is a marker. Suppose if we have the 3 plus 1 dimensional equation. So when we apply the Lie symmetric method in the first time, so we will get the 2 plus 1 dimensional equation. And after that, we again apply the Lie symmetric method, so we will get the 1 plus 1. So, and then again apply the Lie symmetric method, so we will get the ordinary differential equation. Why we using these steps? Because as we are aware of that, the nonlinear partial differential equations are more complicated as compared to the ordinary differential equation. So Lie symmetric works to reduce the independent variables up to the ordinary differential equation. So here, the Lie point symmetry and the here, because our equation is the 3 plus 1 dimension, because x, y, z, and t, and v is the dependent variable. So this is we are taking the one parameter Lie group of transformation method, as we are aware of that, this one parameter Lie group of transformation. And these xi, x, phi, psi, tau, and eta are the infinitesimal generators, and they form an infinitesimal generator. V is xi x, dou x plus phi, dou y plus xi, d xi, tau, e xi, these, the Blumen and Comay and the Blumen and Co are also given this form of this equation. So applying, because in our main equations, this one, v triple x y, so we need a 4th time of prolongation. And applying here, I'm just because we are applied this in an applied term, so we are using only the invariant conditions, not to analyze the method of the Lie group of transformation method. So I'm just taking this invariant condition and apply because we know that these are the extended coefficients eta x, eta y, eta double t, eta xx, and putting the value of the formulation, mathematical formulation into it. So we will get the determining equation. So we will get this, the determining equation after the equating the higher power of v. So we will get these are the determining equation, and we know that these are the determining equations. So we will show it. So this is the important. So on solving the above determining equation, so we will get the desired infinitesimal generators, because xi x is corresponding to x, and this is corresponding to phi, psi is corresponding to z, tau is corresponding to 2, and here eta. So my work is to finding the analytic solution in terms of in this independent functional parameter, because here the arbitrary function method is here. If you see that there are the 5 independent functional parameter, f1, f2, f3, f4, f5, and they are the 2 constants c1 and c2. So we transform this into the vector form. Suppose how to write the v1, because if you see the c1 is here xi x, so we write x by 3 del upon del x, and c1 del upon del y, here this one, and again, and this one. So we write corresponding to c1, so we can write the vector v1 this like, and similarly to v2, and similarly for the other 5 arbitrary constant parameter. And we operate the Lie brackets, and these confirm that if the vector is this form, the skew symmetry, so this form is if you are getting the solution, then the Lie bracket is confirmed, so we will get the closed form solution. So that's why we are saying that the analytic solution of as well as is a closed form solution. So I'm taking some linear combinations of the vectors. Suppose we are taking v1, v2 plus v3. So I'm just taking the 10 combination. It may be more than 10, or it may be more less than 10. You can check by the optimality, but I'm taking the linear combination of this vector to finding the solution. So suppose if we write the solve by V1 because it is already this. So x3 del upon del y. So we write this equation into this form in the Lagrangian characteristic equation. So dx upon x upon 3 dy upon y, this one. And we know that this is the Lagrangian characteristic equation. So we can solve by this equation. Suppose dx upon del, so we will get x, dy upon dz, dz upon dt. So we will get this form of solution. So these are the invariant. And so this is the similarity solution or invariant solution. So here we write, so we having the 4 independent variable into the 3. Okay, so these are the sum. And putting this form into the main generalized BKP equation, so we will see that this equation is 2 plus 1. So here z is removed, but z in the form of x in capital X in z, capital Y in z, and capital T. So this is the invariance invariance property. Means first we have a 3 plus 1 dimensional equations, and then applying the least symmetric method, so we will get the 2 plus 1 dimensional equation. Now again applying the least symmetric method to finding the infinite symbol generator. So here these are the infinite symbol generators. Because this method is very complicated, so it takes time, and you will check by the inbuilt program in the Maple software, and you can also check by hand calculations. So here we see that there are the 5 arbitrary constant in A1, A2, A3, A4, and A5. So the main task is how to handle these equations, because they are the 5 the constant parameters A1, A2, A3, A5. So we choose here A1 equals to A2 and other constant 0. And you have up to you how to handle this equation. You are taking the other all are non-zero and taking 1 or 2 non-equals to 0. So I'm taking A1 is equals to A2 0 and the others are 0. And for these characteristic equations, as we have done earlier, so we will get solving this dx upon dt, dy upon dt. So we will get this form of solution. And here the capital V form of this. So this solution into the previous equation, this one equation. So you will see that we will get the 1 plus 1 dimensional nonlinear differential equation. Again, we apply the least symmetric method and finding the infinite symbol generators and putting this here. So we will get this is the ordinary differential equation. So that is a very beautiful method, a powerful method by using the least symmetric method to get a ordinary differential equation with the higher dimensional 3 plus 1. So you will get the ordinary differential equation. So that's our task, how to reduce in the analytic way. And how to find this nonlinear, because we know that the ordinary differential equation as easier to solve as compared to the nonlinear PDE. So here I'm taking the particular solution, this type of how we can take this form of solution, because there is no direct there is no method to solving this. This is a highly nonlinear ordinary differential equation. So I'm just taking the polynomial form of solution. Suppose we have here h is a dependent variable and derivative with respect to is w. So how to find this type of solution? Suppose I am taking the polynomial form of, suppose as w is equals to means a plus bw plus cw square plus the higher order 3 and the rational form d upon w upon e upon w square and so on. And putting this polynomial form into this equation and putting and then getting the coefficients of the a, b, c, or d. So you will get the 2 solution. It may be occur 3 or 4 solution, or maybe more than 6 and 7 solution. So because here finding the 2 particular solution, so putting this solution into this here, and this h substituting this value into in the previous one because h is there, so putting s, and after we will get capital V, and so you will see that in the V. So you will get the solution in the form of, because in our solution x, y, z, and t. So this is the solution in the analytic form. and it is confirmed 100% verified our main solution. Similarly, we can find the other solutions. Now, the important task to show the dynamics of the obtained solution. So putting here the value of A1, A2, you have to choose the appropriate parameter to finding the solitone form of solution. So here we the multi-solitone wave profile for the solution 36. And now we take the another case for the, because I am choosing the 10 linear combination, but I have to show only 3 and 4 solution form solution V1 plus V3 here. So here the V1 plus V3 is form of this, and solving this equation. So you will see that the small v in the capital V, the form of this one, this is the integral form of, and the in terms of independent functional parameter. So it is very rare to find the analytic solution, the in terms of independent functional parameter and with the integral form of. So putting this solution into the main equation, so you will get again the 2 plus 1 dimensional equation. This is the reduction equation 2 plus 1, and applying the least symmetric method on this, finding the infinite symbol generators, the form of this, and solving this equation. So we will get another solution, the form of this solution, the 3 times reduction. So 3 times reduction, so you will get the another ordinary non-linear ordinary differential equation, and again applying the particular solution by using the polynomial form of solution. And there is another technique to find the analytic solution. So you can apply the generalizer exponential rational function method, a unified functional parameter, a rational function parameter, tan hyperbolic method, and other methods are. So now by using the substitution method on this one, so you will get the solution of this form of. So this is the 100% true, and the solution here, the integral form of the in terms of function. So it means the function, so you can choose, you have a choices to choose as a rational function, as a trigonometric, as a hyperbolic solution. So this solution is satisfied the main equation. So this is the beautiful another 3 dynamical structures. Now we take another. So by using the least symmetric method, so you can find the infinite analytic solutions. So it's you have a choice how to handle the handling the infinite symbol generators. So the same technique we can apply. So we can here the 3 independent three particular solution, and the in terms of independent functional parameter. So it is very rare the researcher working on to find the solution, the independent functional parameter, and I am taking as not take as a constant and not a 0. So how to show the dynamical structure form of this form of the elastic interaction between this curved side shape of the solitone, and another form of solution, this form of. These are the another. So I am trying to find the 10 to 15 solution for the main generalized BKP equation. This is the parabolic, the solitone form of solution. Now we also apply the least symmetric method on the another variable coefficient 2 plus 1 dimensional BLMT equation. It is here the we taking as a variable coefficient and finding the infinite symbol generator. I'm not to show how to apply the least symmetric method. I'm just here to show these the form of the solution of the 3 plus 1 BLMT equation with the variable coefficient. So this is the beautiful dynamics for the solution of this equation, because here this is the G2 and G1. G1 is the function of X and G2 is a function of T. So you have a choice is what you have to choose. So I'm taking the G1 is the 3 exponential in the form of the 4 exponential, and then we can plot this type of dynamics. And there are the several authors working on these dynamics on the solitone theory, because the wave equations depends on the solitone form of solution. And these are the lumps form of solution. We are showing that. These are the contour plot and the 3D forms of solution. And this is also the beautiful, the rock wave solutions. It is very rare to find in terms of the solution. And we are also applying what is the bridging of the mathematical visualization and the real methods. So here to show, these are the pond types. So we show that this is the drop of the water, and the parabolic waves is the rainbow shape, and the cyclode is a disk. So we have to bridging the gap between the real analysis and the obtained solution. And we also tackle these types of solutions. We have already tackled these equations. And this is our research group. This is my wife, and these others are our wives. So yeah, sorry. This one. So these are the main selected reference, Blumen and Comay, Blumen, Jedicolic, and we also referred the Blumen and the Stefanenko, the symmetries and the integration method for the differential equations. So these are the some selected reference. Thank you for. Yeah, any question?
Okay, thanks, Doctor. Any question? Oh, you've got
Doctor.
Sorry, ma'am. No, Mathematica having no software. The Maple is inbuilt software, but I am also solved by hand.
Use to find the solution Maple.
Solution. Not the some symbolic computation with the mathematics.
Mathematica, yes.
We have to form your own program how to find the solution.
You check.
It is not easy.
You check the solution or
Yeah,
take
we
into
have
consideration.
checked,
No. It is limited.
Sorry.
Show figures is solution is limited.
I am just here showing the for the three combinations of the vectors, and you can find because we have a choices because there are the 7 parameters, so 5 in the independent functional parameter and 2 in the constant coefficient. So we have a 7 vectors. So you have a choices to take the linear combination v1 plus v2 v2
I know.
plus v2 v3. That's all.
Thank you very much. I want to give one comment and one question. Comment is that you mentioned some books, actually, but I did not see Ovsyannikov's book. Because Ovsyannikov, he published book in 1962.
Yeah.
Then it was translated by Blumen.
Yes, yes.
And Peter Olver, he wrote this history very good in his preface. So.
Yes, you remind me earlier.
Okay.
But
Please
I just
put
take
it
care of
name
that.
too.
I just take care of that because I am just to inform the student. So we have the limited because if we are given the 7 or 8 books to the student to read this, so it is not easy for the student. But in the future, I will take care of that.
Ovsyannikov, sorry, after Ovsyannikov's book is 1978.
Sure, sir.
Peter Olver book is 1986. You know that. And the first book of Ovsyannikov, it was in 1962. It was translated by Blumen.
Yes.
So then it is a comment, right? So the question is, in first equation that you started studying, so this is many arbitrary functions because it is infinite dimensional Lie algebra.
Yes, yes.
And usually for infinite dimensional Lie algebra, it's better to use group foliation because it reduces to finite dimensional, and then it is easy to work. And for example, you talked about optimal system for infinite dimensional system, infinite dimensional Lie algebra, it is not possible to do. So then I recommend you to do it.
I will try. I will take care of it.
Thank you.
Yeah.
So I have a general comment. You showed us exact solutions from the Lie symmetry method. There's other methods we've heard about.
Yes.
Nowadays, it's easy to produce
Yes.
explicit solutions. What is still hard to do is to find physically interesting explicit solutions. If you look at your examples, you will see that most of your solutions have singularities all over the
Yes,
place.
yes.
They are not physical solutions. Okay, so the way we should approach this is we start with the scientific problem. You have one of these equations. It comes from some physical model. There are certain questions you would like to know scientifically about the equation, about the behavior of solutions. Those questions will inform the type of method that's most appropriate to use to solve the equations. And the results should be physically meaningful solutions. So the problem is the literature is flooded with papers where people are just computing exact solutions that have little or no physical meaning. And it's hidden in your graphs because your graphs do not show the singularities properly. And so it gives the impression that you're finding nice solitary wave solutions when you're not. This is a criticism not just of this,
Yeah.
but in general. Okay, and that type of approach really nowadays should be replaced with a more thoughtful approach where it's the scientific problem that you're interested in. What kinds of solutions are physically interesting for those particular equations? Then you pick the method that's going to get you there. Otherwise, I mean, you can go for years, for decades, producing more and more solutions of your equations, and most of them will be physically uninteresting. So what's been accomplished? Very little has been accomplished beyond just computations. So I implore everyone to try to elevate the quality of work being done in this field by tackling real scientific problems and not just applying, our favorite computational method, whether it's Lie symmetries or the unified extended method, to some equation just to get some explicit formula. It's just easy but it's uninteresting scientifically. Okay.
Yeah, last night I have discussed with you and you informed me the useful and the informative talk. So in future I will take care of that, and I'm choosing some physics, mathematical physics background, and to introduce into the new research paper.
At least find solutions that are non-singular. So they have some chance of being.
But in the solitary form, so we need a singularity. If you to show.
No singularity. Physical equations do not have singularity, period.
Yeah.
So it's the opposite of what you said. We don't want singularity. We want no singularity. We have really smooth solutions for some boundary conditions, mathematical decay conditions, or that meet some physical criteria like finiteness of energy, or for which the solution is stable. My guess is most of these solutions, even if you somehow take them seriously, are unstable.
Okay, thank you so much, Guy. I need to cut you off now. Thank you. Okay, our next speaker is Matlo Kubane.
Yeah, I noticed you let me show some singulars. All the ones he showed were singular. It's these lights. But it's an important part of the problem for delineating the solutions that are these non-singular. That's one way, a single wave solution. It's a single wave.
Well, I know the simulated solution. So I said there are two waves. I know the simulated. I'm interested in the two waves. On the laptop. I want to see how they interact. I want to see the instability.
Okay, thank you. Can we start now?
Okay, thank you. My name is again. Yeah.
So I'm going to talk about the title called Adaptive Rock Paper Scissors Game Enhances Eco-Evolutionary Performance at Cost of Dynamic Stability. So in this talk, we're gonna cover research question, and I'm gonna give a little bit of background of this research, and I'm going to present the model and show you results and a conclusion. So we developed a new rock, paper, scissors game that focus on eco-evolutionary dynamics to study strategy and trait evolution. So the game is integrated from evolutionary game theory and adaptive dynamics so that we can investigate how adaptive strategies change through trait evolution and how such adaptive changes affect the numerical performance of each strategy. So the rock, paper, scissors game is a two-player game with three strategies: rock, paper, and scissors. So there are two general theoretical frameworks used to study the rock, paper, scissors game, which is game theory and evolutionary game theory. But allow me to speak a little bit about game theory. So game theory is the study of mathematical models of games. But game theory doesn't consider games the same way we are used to in common life. And it certainly doesn't talk about computer games. So instead, game theory is considering games as strategic interaction between self-interested participants. And for that reason, game theory is important in economics, computer science, politics, psychology, and evolutionary and biology and ecology for me. So in game theory, the rock, paper, scissors games is normally represented by a payoff matrix. And this payoff matrix here, each entry of the matrix represents the payoff of row strategy player 1 against column strategy player 2. So the players receives a 0 payoff when there's a tie. Otherwise, the winner receives a benefit B naught and the loser incurs a cost C naught. So in evolutionary biology and ecology, the payoff matrix is the proxy for fitness of each strategy. So fitness is the survival and reproduction of strategies. So the evolutionary rock, paper, scissors game portrays the cyclic dominant structure between three fixed strategy where rock beats scissor, paper beats rock, and scissor beats paper. So the cyclic dominant structure is a common structure in ecology, which is one of the key factors contributing to ecosystem complexity, to species competition, and even coexistence. So this research is motivated by recent studies of evolutionary game theory that explored the role of mutational jump between strategies under fixed payoff matrix. But however, in real life, strategies can co-adapt with each other. So to allow each strategy to adjust its payoff, we deployed adaptive dynamics to model how strategies change adaptively through trade evolution. So adaptive dynamics is a theoretical framework for studying trade dynamics from incremental mutation and selection due to eco-evolutionary feedbacks. So in this part, I'm showing two matrices. You can see matrix A and matrix A prime. So these are the 3x3 matrix, but matrix A is a payoff matrix of evolutionary rock, paper, scissors game, while matrix A prime is the matrix which we develop in this study, which is the payoff matrix of the adaptive rock, paper, scissors game. So the difference is in matrix A prime, the benefits and costs are now functions of trade. So we consider two-dimensional trades. So, and I explained here. So these are the Gaussian function in adaptive dynamics to explain as the function of trade, to explain the benefits and costs as functions of trade. So the rock, paper, scissors game with matrix A prime is now presented in two logic steps, which is the adaptive, the dynamics of trade density with trade mediated payoffs and adaptive dynamics of co-evolving trade. So the dynamic of strategy density with trade mediated payoffs are captured by the trade mediated Lotka-Volterra equation. I'm sure some of you are familiar with the Lotka-Volterra, which is the equation describing the dynamics of biological systems. So we make some assumption there. We assume intrinsic rate of trades, and we also assume self-regulation of each strategy against itself to be one. So this vector here is the one that I'm talking about. It's one. And here the adaptive dynamics of co-evolving trades is captured by the relaxed canonical equation in a two-dimensional trade space. So the canonical equations of adaptive dynamics are the differential equation describing how trade changes over evolutionary time. So we are calling it the relaxed canonical equation because we have made some assumptions in there, but I won't explain it in detail. So both the trade mediated Lotka-Volterra and the relaxed canonical equation are solved. We solve them numerically using simultaneously and numerically using Python. So this system now we call it the population of individual playing 3 strategies in an adaptive rock, paper, scissors game, and is described by 3 time varying state variables and 7 parameters. But for the purpose of this work now I'm presenting, we assume the growth, benefit, and cost of strategies to be 1. So we only consider the growth, the benefit, and cost of the trades instead of the strategies. And the assumption when these parameters are not equal to 1, we are exploring them in a subsequent study where we are studying the evolution of cooperative behaviors. So the results here is when the strategies are not changing adaptively, when mu I is equal to 0. And figure A, B, C, those are the dynamics of strategy densities. So when strategies are not changing adaptively, this part here, A, B, C, is equivalent to evolutionary rock, paper, scissors, which have been explored before. So, but what we can see is in figure A, I have made the growth, the benefit and cost to be, the growth and cost is 0.9, 0.9, and that one is 0.5. But here what I'm doing is I'm making the benefit high and I'm making the cost low to see the behavior here. So I can see that now the strategy densities have increased in their performance. But here, when I'm making the cost very low and the benefit, when I'm making the benefit low and the cost high, we can see that now the strategy density are affected and the density have decreased. But this is also supported by the long-term behavior of the system by varying each parameter while keeping the others fixed, which is some kind of a bifurcation diagram. So D, E, F are bifurcation diagrams for each parameter. And in overall, we can say that increasing benefit and growth of our trades improves the strategy densities, but increasing the cost hampers the numerical performance of those trade densities. My red. Or the red line. Or the red line is the densities of the rock, of the paper, the green one, and of the scissor. Yeah, sorry if it doesn't show, but maybe some people can see. So here, this is the dynamic of strategy density with trade evolution. Now we are allowing strategies to evolve. But you can see in figure A is equivalent to evolutionary rock paper scissors game. So no strategies are allowed to change its trade there. So we compare it with B, C, A, and D. So in B, we are only allowing paper to change adaptively. And you can see that the rate of the strategy density of the paper only increased if we allow it to change adaptively. And then if we are allowing the paper and the scissor to change adaptively and keep rock fixed, now the paper and the scissor have increased, but there is something else. Now the system is unstable, it's no longer stable. And if we are allowing all of them, it shows that now that is unstable, but their performance have increased. So this is the bifurcation for when all the bifurcation of the long-term behavior of the system by varying each parameter while keeping the others fixed during the trade evolution. So these are the bifurcation. So figure A, B, C are the strategy density against each changing parameter. So we can see that now strategies increase to value 1, that is the carrying capacity, as the growth increases. So strategy density also increase, but destabilize with increasing benefit, while the stabilizing and decreasing, while it is stabilizing and decreasing to 1 as the cost increases. So here is the adaptive dynamics of co-evolving trades, because I said this model is presented in 2 logic steps. So I presented the one where we're talking about the Lotka-Volterra, or the density of strategies captured by the Lotka-Volterra. Now we are presenting the part of the adaptive changes of co-evolving strategies captured by the relaxed canonical equation. So figure A, they illustrate the evolutionary trajectories in the 2-dimensional trade space. B is the average strategy density to each other in the trade space versus the average trade densities to origin. C is the average benefit versus average cost in the plane. So this game exhibited diverse evolutionary trajectories, but here I only showed the closed limit cycle. And the evolutionary trajectories emerged in the game exhibit greater benefit than cost. And this is the long-term behavior of the system by varying each parameter while keeping the others fixed. So figure A, B, C is the trade coordinates against each parameter. Figure D, E, F, those are the trade distance to origin against each changing parameter. So what we see is there's a little effect on the trades coordinates and trades distance or difference to origin. However, the trades coordinates and distance to origin start to diverge as benefit increases while increasing as the cost while increasing cost tend to destabilize and constrain trades close to origin. This one. So from this whole result of this game, we have observed that the adaptive rock, paper, scissors game approaches steady state faster than the evolutionary rock, paper, scissors game. And the stable coexistence of all strategies in the evolutionary game can be easily destabilized in the adaptive game. Also, the strategies that are allowed to adaptively change their traits perform better and achieve greater strategy densities than those which are fixed in the adaptive game. And lastly, the co-evolving strategies in the adaptive game exhibit complex and diverse attractors in the trade space, but exhibiting greater, positive payoffs with greater benefit than cost. So in conclusion and summarizing everything, my take-home message from this presentation, even if I was fast, is strategies in the adaptive game enhance performance but destabilize the eco-evolutionary dynamics. And this is the end of my talk. Thank you.
Okay. Thank you. We still got a few minutes for questions.
Yes.
And this is advice to people. His life story is very interesting. First of all, he's the only person that received both the Nobel Prize and the Arbor Prize. And it's interesting that he worked for game theory, got him the Nobel Prize in economics, but he did some remarkable work in differential geometry with his famous isometric bedding theorem. So, and he had this long, you must have seen the movie Beautiful Minds, where he had some real psychological problems. He became better, and then the end of his life was also a bit tragic because he received the Nobel Prize. He went to collect it with his wife in Norway and came back to New York, and they were taking the taxi and on the famous New Jersey Turnpike, they ended up in an accident and they died. But the other interesting thing is he only published, well, I shouldn't say only, he published just 26 papers. It's quite amazing. So it's something that we should think about.
But no, we didn't publish things. That's the problem. There's no space. Just interesting aspects of it, right?
Okay, that's a small question. Not your metrics, the one you were showing, is it always on your first slide? It's equivalent. One step, sorry. Yeah, go back.
Or are you talking about this one?
Yeah, that one, the payoff matrix. Is it always that?
Is it always?
Yeah, so like that.
No, it's not always like that. It's not always like that. You can, in evolutionary game theory, you can change the diagonal because the rock paper scissors game is a non-cooperative game. So we can change and see the effect of self-regulation of strategy against each other. It's not always about this, but majority of them is like that. Oh, there is a question there.
Not really a mathematical question. I'm just curious to know if you know any examples of what this rock, paper, scissors game looks like out in the wild.
Maybe I'm not understanding the question. How it looks like out in the world.
Like follow or something, but what is the physical
Okay, no, they are like, yeah, okay, I think I understand the question. So they are like a lot of examples, at least I know few, which are following this structure of a rock, paper, scissors game, where no species is winning in the game. It's just cyclic like that. That's why I said the cyclic dominant structure is common in ecology. For example, like the cyclode lizard. So there is this example of cyclode lizard, and then the example of E. coli bacteria. So they follow this kind of a structure in real world. No, that's
What is the lizard doing next?
no, I'm okay. No, I mean like you will have like 3 lizards. This example, okay, I don't want to say things that I'm not sure about, but those examples are there. I don't know how to explain it now. Yeah.
Lizards love rocks and water.
Okay, that's not.
For a rock, I write.
Yeah. Yeah, but I'm happy to show you those examples that are following the rock paper, but they are there.
Okay, thank you. I
Yeah.
think it's time for now for lunch. Okay, you can go for lunch now. Oh, it's 1. Okay, sorry, you must come back here at 1 o'clock. Oh, two, sorry. 5 minutes before 2.
Especially the
But we are going
presenters.
late, eh? Everything was
Oh,
late.
thank you.
Oh, thank you. Thank you.
About the nation, George Price and the Nash.
Yeah.
Yeah, I need to sort out something for.
So you can come for lunch around.
Yeah, you can give it.
I'm gonna do, one of my assistant is gonna switch. Yes, but I gave you new mics, so everything is.
Gifts.
Yes, you want to put them in my room?
Oh, are you putting them in the car? Which you're giving them out?
Yes. Yeah, so I can.
Yes, we can. That's the kind. The whole world is.
Okay.
No one's from.
I used to do the thing for the
No. This has already
Yeah.
done the whole world.
Yeah, it's just about to go far. So what I did there is, can I show you?
Okay, no, it's fine, let me use the bathroom.
Okay.
You can show me, but I'll leave, let me just use the bathroom. I'll come.
That's not bad.
But for your, I can be here for the session.
Uh,
No, let me do it for you, I don't mind.
Normally it's some groups.
No, I can do it, so. Yeah, I'll be here, I'm staying in.
Hey, how are you? Let's see what you have.
Oh, because I saw it. He said, why didn't you? Yeah. Yes. Well, I think it's fine. What that's your issue? Yeah, yeah. What did he say when he's not coming? Okay, all right. Okay, no problem. No problem. Okay. Okay, right. Oh, it's all the data. It's good when you have this. It's much more. Yeah. So. No, we came back. So for one kind, all the kind. Okay, thank you. No, I think we can leave them for I think they know what the program is right now. I'll take care of it. Yeah. Thank you. Yeah, I saw when I left. I'll go. I'll go there for actually. Thank you for everything.
Okay. Yeah.
But the people disappear. Why it was done?
So yesterday, the camera.
Yeah,
So he was the head of council. At first, for a long time. Yeah. And then I thought I think he became retired.
Because it was.
Nobody did say hello to me.
Oh, isn't it? I mean,
It's
it's.
very humble.
Yeah.
I mean, yeah, for example, we asked me tonight, can we exchange jackets to multiply jackets?
It's a big job, eh? I mean, he was challenging, Betty and so on.
And you know, it's, yeah, I think the next one who actually went on stage, confessed that it's HIV.
Yeah. That was one of
It was
the.
very controversial.
Yeah.
So I think because of that, then many people were able to come out.
Yeah. And that's why he openly challenged, you mentioned,
Yeah.
double Betty.
Yeah.
So I thought he, like, from, now, here is your chance.
And also, yeah, but it they're very normal. Really enjoy working with them.
Many years ago, Faisal was looking for a house. And he's not in the city. They didn't know that. They went to sleep. But. Except for that. This is
With our chairperson. They are not
May I please put on mic? Okay, yes, just like that. That's all. Thank you so much. Cool, thanks.
Then you should change. Let us practice on time. You have to introduce yourself and then you
No, it's not being online.
Then the people rest, then I don't know, we should know what's the timing for the evening.
5:30.
For 6 o'clock.
Sorry?
We leave, to be there at 6, we leave at 5:30.
Well, usually it was possible to fix,
What that is 6.
later.
So if there's no talking, if that doesn't end, maybe you can have already like a short session to the. So that we don't give everything for Friday.
Every Monday night. I mean, I'm not into Wednesdays.
Yeah,
How do you pronounce can? Can Hui. Can.
Yeah.
Can Hui.
But I'm just saying.
That's just fine.
Oh, that's it. For them, there are some students who want some help, so we can have a small session for them. There is, yeah, waiting for the bus. Oh, I can't be.
Good afternoon, colleagues.
Good afternoon, colleagues and students. It's a minute after already. It's time for our next plenary. My name is Lazarus Rundora. I've been asked to chair this session. Our next plenary speaker is Kang Hui. The talk is on some differential/difference equations in mathematical biology. Over to you, Professor.
Thank you, Lazarus. Thank you, Professor Moyer, for inviting me to attend this meeting. It's very interesting. I have to confess that I'm not 100% follow everyone's talk. Can you give me a 15? Give me a shot at 15 minutes. Yeah. So let me first thank acknowledge the kind of research funding agencies and so on. So currently we're running a project funded by European Commission and also UK NERC grant.
This one is biodiversity building blocks. So basically we package biodiversity data into meaningful policymaker can read indicators. And for the UK grant, we are running this called Glyterus, Global Long-Term Insect Declines. Basically, it's a meta-analysis of insect declines. So in ecology, we are dealing with a range of spatial scales cannot compare with cosmology, and we are all in a very narrow range of spatial and temporal scales. And in ecology, we acknowledge that multiple processes interplay gave rise to the different patterns, and those processes typically have a very distinct spatial and temporal scales. And it's very important to know the underlying processes of your system, because quite often those processes operating at the correct temporal and spatial scales will come up as the important ones. So that let me just try this one. This is our way to kind of understand ecological complexity. So we understand that in nature there must be some kind of mechanisms give rise to different patterns, and we go out, we collect those, we observe and collect those patterns using samplings or observations, and from that we summarize that into structures, patterns, and relationships between different parts of the system. And from the other side, we also have, based on our understanding, we have hypotheses. Using hypotheses, we develop models, and from the models, we can have predictions and simulations, and the model will generate structures, patterns, and relationships. And we use a statistical approach to test whether our model is robust, reliable, or if it's not rejected by the data, then it's a candidate to explain the patterns in nature. So this is the kind of a summary of the role of the scale matters in natural phenomena. So in our group, we have 4 research topics: biodiversity patterns, population dynamics, evolutionary games. Matlu has presented his PhD project, and then also adaptive networks. So regarding biodiversity patterns, so basically what we do is we go to the field, we observe a community. Community is just a bunch of species. Okay, so you can have plant species, bird species. You can quantify those species by, okay, each species have a set of traits. You differentiate them. You can also count how many individuals are there. And then based on this understanding, you can quantify the similarities and the dissimilarities between communities. And matched with Earth observation, which is the remote sensing kind of data products, we are able to interpolate some biodiversity features. So for instance, this is mapping the forest tree symbiotic status of 3 different kinds. This we can also, based on those biodiversity components, you can also estimate potential indicators that is relevant to managers, policymakers. For instance, this one, we are predicting invasion probabilities. So in a community, especially if you count native species against alien introduced species, and how the potential aliens can impose impacts to the native species. And you can also map it. And from ecosystem kind of structures, you can also estimate ecosystem services. So we all rely on ecosystem services. So this is kind of the estimate of carbon density globally. And from this, we can have lots of policies, relevant policies regarding potentially, can we restore certain natural forests? to mitigate climate change impact and so on. And in South Africa, we can also do lots of kind of a localized regional studies. So this one is about dragonflies. So ecologists went out, so they survey at different points. So they quantify the assemblages, which is a list of species in a local area. And then they can quantify, so you can consider that as a species set. So you can have intersections, unions of those species sets, and couple that with Earth observation, remote sensing kind of layers, then you will be able to map the dissimilarities and the similarities of those species assemblages. The second topic, population dynamics, I'm just gonna use actually one of the chapters in this book. It's a bit messy, so I'm gonna, so normally what we consider the crucial processes in ecology is basically birth and deaths. So when we're talking about population, the population is just at a time and space, that's a group of individuals. And each one is born through an event and also gonna die. And from those type of linear birth-death process, Markov chain, you can derive this type of differential equations. And for kind of textbook introduction of ecological models, you typically have those Martunian and the logistic equations, where n is population density of some kind of target species at a location x and time t. And r is the intrinsic growth rate. So typically you can consider r is basically just the beta minus mu. Beta is the birth rate, mu is the death rate. So the reason why there is this logistic growth is in finite environment with finite resources, you can't kind of grow infinitely. So you have to have a carrying capacity to keep everything low. So, and this type of differential equations, you can also explore them using difference equations. So for instance, for the logistic equation, you can explore in this way. You have a time lag one, and you can put your R into the brackets, which this is called a Ricker model. So when you explore the difference equations, there are a huge variety of dynamic behaviors. There's another one is called meta population dynamics, which is, if you imagine due to habitat loss, you have lots of different remaining habitat patches. Your species are living in those patches, and then they can move between those patches and save each other. So this is a kind of standard Levens model presented by Richard Levens, which is also a Russian scientist in the 60s, and it's a very simple model. So you have probability, you can consider this P as the proportion of patches being occupied, and is equal to C, colonization rate of the current meta population size, which is the proportion of patches occupied, 1 minus P, which is colonizing those remaining empty ones. So this, you can consider these two are basically encounter rate minus extinction rate. So the existing populations also experience extinction event. And you can also study this using this moment closure approach. In physics, it's also called pair approximation. Basically, you quantify global density and also pair densities. So if I randomly pick two adjacent pairs of patches, what is the probability of both patches neighboring to each other being occupied. So you can see the structure is also very similar, where Z is basically the number of neighbors each patch can have. Here is the local densities. So if I know a pair is empty and occupied, what is its chance for this empty one's another neighbor being occupied? So the closure approach is basically we have to drop this additional ones. Otherwise, you have to keep writing more and more equations. It's not closed. Sorry? Z. So in a lattice environment, okay, you have a regular grid. Z is a constant. But you can parameterize that for a real network structure, patch network. Okay. Diffusion, traveling waves, we have lots of talks in this meeting, so I'm not going to mention that. So integral difference equations, basically, for instance, I can explain this as this is at location X, at generation T plus 1. So normally we work with insects, so with discrete generations. Because with continuous generations like humans, it could be quite difficult. So this is generation T plus 1, population density. Population density is number of individuals per square kilometers and so on. So 15 minutes now. Cool. Of course, N can also be population size. When we know what population we are talking about, we also use N for population size, which is number of individuals. So the G function here is basically a density. This is density dependent recruitment. So how many next generation can I produce from generation T at location Y? And this K is basically a dispersal kernel, which describes the connectivity. So one propagule, which is one individual, what is its chance moving from Y location to X? So this can also be parameterized. You can measure actually the kernel function, the dispersal kernels. And this is a integral difference equations, and you can also have this traveling wave solutions eventually for simplified systems. Okay, this is kind of a very wordy one. So what I want to show is just in populations, of course, we have labels. Okay, so we label species, and we can partition species into, let's say, seeds, seedling, adult plants. So there are those divisions. We divide them, and we can also say this is a cat, that is a dog. Those are labels, and the labels do not exist without humans. Okay, so that's a kind of artificial construct of us imposed to this natural world. And so, of course, then we can, but that's part of the research is when you face a complex dynamic systems, what do? You divide. You divide your system into different types. So you can say, okay, I have capital N number of different types, and I quantify each one's density in such a way, very similar way. And when I combine them together, what is the total population dynamics? X is the space variable. At the moment, so later on, X will change its meaning. Okay. So some previous work we managed to show under some kind of constraints that there is this traveling wave solution, which is related to this kurtosis of the distribution of your kernels. Because the kernels, typically we use a Gaussian kernel where kurtosis is literally 0. So this part disappeared, and back to this the Fisher's traveling wave solution. So that's population dynamics, and then I'm going to move on to evolutionary games. So because Matlu has already presented his rock, paper, scissors, we also have lots of prisoner's dilemma games. Of course, there you have lots of those tragedy stories in this whole field. You have George Box, you have Price equation. So behind all equations, somehow there is a tragedy there. So Darwin proposed this approach to explain in some specialized system. So this is one system. If you have a hiking, go out in the Stellenbosch, you will be able to see this. This is in around Stellenbosch. So you have the longest proboscis to body length ratio of the fly. This is the highest ratio of fly in the insect taxonomy. And this one is the orchid, and it has very long floral tube. So the question is, why in such a system you have such extremely elongated traits? So this is what I mean, life history traits, okay? So the traits is the weaponries, it's the means for species, individuals to engage in interactions. When we're talking about biotic interactions, what do we mean by that? There must be some kind of a contact, and there must be some exchange. And those exchanged benefit and cost, for instance, for this one, so the pollens of the flowers will be in the abdomen. And when the body contact the petals, it will deposit the pollens. So that's the exchange. And in exchange, the flower will contribute the nectar, will be consumed by the fly. So Darwin proposed this idea, which is, if the flower is very short, the bee can just simply suck all the nectar without deposit the pollen. So there is a selection pressure for the flower to grow in longer and longer tubes. For the bee, if your proboscis is very short, of course you will deposit because you want to suck the nectar here. Of course, your body will deposit pollens to the flower, the top of the flowers. Great, you contribute to the flower. But if your proboscis is too short, you can't suck the nectar. So you're also under this directional selection pressure to getting your traits getting longer and longer. So then that leads to this co-evolution, this arms race between the two species to prolong, to elongate, and to allow their traits to elongate. And we actually, in South Africa, we can see there are very interesting patterns of these two species along this is Cape Town, where we are here. We are roughly here. So if you go up, you can see the extremes. So shorter, close to Cape Town, further north, getting longer and longer. And they are, roughly speaking, all paired, actually. So this is at the different places. This is the proboscis length. You can see the proboscis length is growing up. And the interesting part is, if you explored multiple populations, you found actually the proboscis is slightly longer than the flower tube. And this is one population. You can see these are the flower tube. This is a histogram of the flower tube, and this is the trait length. The trait length of the longer ones match with each other quite nicely. So the question is, can co-evolution explain the emergence of this trait matching? And it's also have this interesting polymorphism, so which means you have multiple peaks of the trait distribution within the same population. Okay. So this is the type of model that we use. I think Martin has already mentioned. So say we have a population and one species one in this population. So typically your reproduction output, or we can call this fitness, your performance or fitness is proportional to your population size. Yeah, so for instance, you can consider this as how many offspring I can have, how many individuals are there, so that drives the dynamics, proportion. So you can imagine what a logistic equation looks like. That's a very simple. Invasion fitness. It's a key thing we are trying to evaluate, which is if I bring in a mutant. So this mutant is very rare, so it's not going to be with a positive population density. It has a population density. This mutant has a very infinitesimal population density, literally zero. You can consider that as zero. So when I bring in this mutant into this co-evolutionary game, what is its performance? This is evaluated against the current population. The current population's traits, this is one species, this is another one. Okay, so you have, because this is a mutualistic network. So when this population dynamics has reached equilibrium, this F1 is zero. Yeah, it cannot grow, so the population is stabilized. At that point, I bring in a new mutant into the system, and I want to see whether this mutant can perform better or worse than the resident population. Okay, so if the F1 is greater than zero, because the resident one has F1 is zero. So if the invasion fitness is greater than the resident fitness, this traits or this strategy represented by the mutant can invade this population.
So here X and Y are some arbitrary also.
Yeah, those are the trait values. Like for instance, the proboscis length, floor tube length.
For different values.
Yeah. And so in Martu's case, he formulated using some kernel functions for this type of thing. We can also use this very simple one, benefit minus cost. This is basically the preference of interactions. If I encounter each other, do I like to interact or not? And from this, we have invasion fitness. So what I'm trying to say here is you can have lots of different ways to formulate your invasion fitness, okay? From the invasion fitness, and you can calculate the partial derivative of your invasion fitness with respect to the mutant traits and evaluate it at the resident trait value. What is this? Selection gradient is driving trait evolution in the system. The important thing is this is actually, the entire thing is actually a function of X. Yeah? Because X prime disappeared after this evaluation. So selection gradient basically is a force drive trait evolution at point X. Then we also have some other things. Curvature is to describe disruptiveness. So you can have situations where in that trait point, any mutations, changing the trait value X to X prime, you found your performance is going down. So that fitness point, that trait represents a fitness maximum. And you can also have the situation where you found everywhere around you actually have a higher fitness. So you're actually sitting in the bottom of the fitness landscape. You can imagine the fitness in the trait space as a landscape. And then you will under disruptive selection. Yeah, so any mutant from this direction, because it's higher, going to replace, going to keep going this way. And this side also going to go in that way. So that's, you can define disruptive selection. And if the population experience disruptive selection, it doesn't mean you're gonna have an evolutionary branching. You're gonna actually have two. Why? It's because once the branching event, the disruptive selection happens, the two populations are having very similar traits. Yeah, because right in the beginning, they're very close, very similar to each other. And normally we understand that two type of individuals with very similar traits cannot coexist. So there must be this further condition called the protection of dimorphism. So they can diverge, but can they coexist? Typically, they can't. You have to, under this additional conditions, to allow them to coexist. Okay, so once all conditions satisfied, you have evolutionary branching. In the trait space, the system will converge to the evolutionarily convergent stable point, singularity. At that point, if it's under disruptive selection, and if the protection dimorphism is assured, it will diverge. So here are a few examples. Okay. So in this system, so this is kind of like standard parameter sensitivity. So you can see in the parameter space, what kind of evolutionary dynamics you can have. So these are some kind of examples. You can have ESS, evolutionarily stable strategies. You have your trace value. Initially, you can randomly assign them. They converge to kind of matching traits. You can also have one is this way, the other one is divided, branching into two. So this actually is what we observed in reality. And of course, you can also have this so-called red queen dynamics. So in the trait space, they're chasing each other. One is this way clockwise, the other one is anti-clockwise in the trait space. So using this kind of computational scheme or adaptive dynamics framework, we can see there is the condition to allow evolutionary branchings to occur in your system. And this is then become a debate in the field, which is if we explore, this is one side is butterflies, the other one is resource plants, plant species. And these are their evolutionary trees we call phylogenies. And if you map which one is intact with which one, yeah. There are hypotheses about what is the reason behind this network structures. So can co-evolution along this phylogenetic tree explain this network structures? So just to summarize this type of a model, let me just check, yeah. So if you want to design a model to describe using adaptive dynamics to describe your system, you typically have two sets of equations. The first set is very similar that you can find in any textbook, which is population dynamics. Per capita population growth rate is proportional to RI, intrinsic population growth rate, and modified by all sorts of things. By what? By biotic interactions. Okay, so you have competitions, you can have mutualism. So here you also have different type of a so-called functional response, which means if I have, so we have limit capacity when we consume things, okay, when we interact. So if I give you one slice of pizza, you're going to eat one slice. If I give you two, you're going to eat two. But if I give you 100, you're going to reach your capacity. So this mainly the consumption rate is plateaued. Following this is a so-called Holling 2 type 2 functional response. And then we also have a trait dynamics. And typically, this is the mutation rate. So mutation rate can be extremely slow. Yeah, extremely small number here. So you can completely analyze your two systems by assuming complete time separation. Okay, you evaluate this all in at its equilibrium. And at equilibrium, you trying to evaluate the trait dynamics. So this will point out at equilibrium which direction is the selection.
How they related? Because A and A.
A is basically the equilibrium. So that's the total time separation when you evaluate it. But we can also allow relaxed one. Why? Because in reality, the mutation rate, even though natural selection has reduced our mutation rate is still not zero. It's a tiny little positive number. So it's not a completely separated system. So these are some kind of simulations. This is a mutualistic network. You have plants, you have animal from the other side. Those is trait axis. The black lines are the trait positions. Those are actual traits. The background is the invasion fitness. Okay, so invasion fitness, which is you randomly throw in a rare trait at this point. It says it's positive. So if I randomly throw in an individual here with this trait value, it will grow, it will establish in my system. But why it doesn't spread to this direction? It's because we only allow incremental evolution. So your trait change, the mutational rates, mutational magnitude is literally zero. Okay, so you can't just shift from here to there. So it's a highly constrained system, actually. So in such system, you can also have scenarios where system can have empty niches. Empty niches, like for instance, those purple ones indicated. So they have positive fitness. If you throw in, if the plants create a mutant, by chance have that trait values, and those individuals will grow, will establish. But it doesn't occur because you only allow incremental evolution. And of course, you can follow up those trait space by introduce alien plants. So that's what we call the alien plants. So basically, is some plant species, maybe not from South Africa. You can introduce those plants to South Africa. It will cause some kind of cascade effects in your trait evolution. I think this one is predator prey. So like you can have plants, you can have herbivores. They can also evolve in certain ways. So the plants potentially will run away. So you can have runaway evolution. So you're trying to escape that trait lock, trait matching. And you can also have those type of red queens. So they're oscillating, trying to match up against each other. So these are also some kind of simulations. This one is demonstrating evolutionary stability. So the traits initially this is evolutionary time scale or time. So it converge to this. So this one is evolutionary branching at this point. It's a fitness minimal, it's split into two. And you can have red queens. And you can have evolutionary suicide. Evolutionary suicide is you initially undergo disruptive selection, you have evolutionary branching, but soon after that, one branch, it becomes not feasible. It cannot survive, so it will die. And then in your system, because we know this is the original singularity, evolutionary attractor, so this branch will, under selection force, just go back to that point. And then at that point, disruptive selection again, die. So have this repeated. It could be no. It's yeah. So this is a trait in the trait space. So at certain point, if you can still check your population equilibrium, the density, your density can reach 0. So that's not feasible anymore. So in the trait space, you're still under selection forced going towards some direction where you can't sustain your population size, your population collapse. So if there are no individuals, there's no traits. So that's why. So this is the canonical equation in a higher dimensional space. So you can have multiple traits to describe your species. I think so there are a set of theories have been developed to study convergence stability and evolutionary stability in such a system. And we're also trying to develop this kind of called Jacobian, because Jacobian of the canonical equation will fully control the trait dynamics. And you can partition that. So this is a Jacobian, and this is a mutational matrix. If it's a higher dimensional trait values and multiple species. And this selection gradient, Jacobian of selection gradient, can be further partitioned into Hessian, frequency dependent, and co-evolutionary matrix. And each has a meaning. So visually you can see those are zeros, those are those 3 parts, 3 species, each one have different number of traits. So the Hessian matrix is describing whether they are under disruptive selection or not. If you want to try to evaluate whether your system is undergo disruptive selection, you check whether the Hessian is negative definite or positive definite. And frequency dependent selection determines after branching, can you coexist or not? Co-evolution, you can see it's all the non-diagonals. Those are the interactions between species. So I'm not going to that details. The conditions. So there are a number of kind of like a typical evolutionary regimes, evolutionary branching, type 1, type 2 evolutionary traps. You can have continuously stable strategy, which is stronger ESS. You can also, of course, have instability in the system. And this is one example. So this is this kind of the typical Lotka-Volterra model. So you have intrinsic rate of growth. N is now it's a function of traits. Okay, X is traits. That's time. So you can have carrying capacities, and the summation is over all the other species in the trait space. So alpha XY is what we call competition kernel. So that is the interaction strength between 2 species. So typically you have to specify this kernel function to follow specific forms. And that is a challenge. And we are in very close negotiations and discussions, collaborations, trying to work out what is actually this kernel form. We normally use Gaussian. Yeah, so it's very nice Gaussian kernels and so on. But the reality might not be. Yeah, so you can have cortex, you can have shapes very much like flat and going down very quickly. You can have there's different type of shapes. You can even have asymmetric interactions. So for instance, body size. Yeah, so you have 2 individuals, the one with a bigger body size can competitively win, or have competitive advantage over the shorter ones. So you can implement different types of competition kernels, carrying capacity, and even including the intrinsic rate of this R can also be trait dependent. So any demographic rates. So all the parameters in such ecological system, we call that demographic rates. So all the demographic rates are trait dependent. Yeah. So from that, we can evaluate invariant fitness. We can partition the Jacobian. We can see the system. So this basically, as demonstration, is in a higher dimensional trait space, the evolutionary branching does not necessarily follow the same direction. Yeah, so your Hessian matrix, the eigenvector determines the branching direction. But it doesn't have to be, so you repeat your history exactly according to the same parameters, same initial conditions, and so on. The branching happens because branching point is a singularity. At that point, you can diverge in this way or in that way. So history does not repeat itself. So this is actually a hypothesis in Darwin's age. So in higher dimensional space, can you have the scenario where a single trait simultaneously diverge into 3 or even 4? We all, if you look at the evolutionary trees, always like 1 split into 2. 2 keep going. But can you simultaneously diverge into 3 branches? And we can show that it's actually, yes, it's possible, but the chance is very low. So these are some kind of simulations, and those are the projection on the trait space. This is time. What type? 2-dimensional space, okay. And this is the three-dimensional trait space. I have some simulations. Let me see whether it didn't show or not. So it starts. This is the trait space. It's branching out. This is just a projection. This is time. It can go all and go that direction. And this is the color indicated time. So it's split, filling up all the resource space and so on. Let me see, where am I? Okay. I have 15 minutes. I actually want to jump to some other very end parts, because I would like to actually invite some potential collaborations. So I just come start from here. So this is very simple. The species I in the population. Remember that those species, it's just a label. It doesn't mean anything, okay? We call that species I, but only we call it. So this is its performance, fitness. The question is, in actual system, this I is part of a set, species set. Which species is part of your system? That's a set. And the set is dynamic. Yeah, so you have a dynamic system where the dimension is dynamic. Your species set is dynamic. It's keep changing its members. Why? It's because eco-evolution is you allow species to diverge or being introduced into your system. You have winners and losers. Losers being kicked out. Winners can thrive. So the system is constantly in transition, in turnover, updating itself. So of course we can simulate it. Yeah, so we assign each one. We have our interaction kernels, and we can also bring in stochasticities, demographic stochasticities, or even including those eto process, environmental process noise, and so on. We can simulate it. Let me just show this one. Yeah, so this is one actual example. So multi-vector model, ST is a dynamic, and you have your population density undergoes a Poisson process to represent demographic stochasticity. Okay, every time you sample it based on its expected population size, And J is community size, system size, it's also called. So in such a way, your NIT is fluctuating. The fluctuation, if it's not driven by biotic interaction, is driven purely by demographic stochasticity. So every time you randomly select a number of individuals, because this random selections eventually will fluctuate according to a Poisson if you don't have preference, if this selection is completely independent from each other. And after you assign some interaction kernels, these are two sets of simulations. You can see this is in the trait space. And the surface, the colored surface, is invasion fitness. So if I put an individual somewhere here, it's blue, it's positive. I just remove all the negative fitness. So if you randomly introduce an individual with this trait into the system, it will die. It cannot survive. So this gives us a very interesting portray of the trait space, of the community trait profile. And the green circles is where the species is. So there is a species here, and the population size is proportional to the radius of the, and this is completely dynamic. Okay, this is just a snapshot. And you can see is sometimes you have very interesting self-organized patterns emerge. So my question is to bring up a dialogue is lots of, or most of biological systems is such dynamic systems with flexible and even latent dimensions. Latent, I mean that we only measure those variables, those species that we can see, we can observe, but we miss lots of other things. So there are lots of hidden interactions we don't know. Okay, but then the crucial thing is there is this issue, flexibility. The dimension itself is keep changing. We have to use a set to keep track of what kind of species, which species is in our system. And we can simulate it. But how do we formulate this in a proper way in using dynamic system, using differential or difference equations? And actually, I mean, just while sitting there in the morning, I got this idea because from one of the speakers from India. I can't really see him. And yeah, Kumar, yeah, Professor Kumar. Can we do this? This is my population density, partial derivative with respect to time. This again, it's intrinsic rate, so that's how many babies I can have, population density. This is one way for me to formulate logical Volterra, so yeah, integral interaction from y against x. And this is population y at time t, its density. Integration. Carrying capacity is also trait dependent. And this is my trait mutation term. And this actually is called evolutionary distribution model. So besides adaptive dynamics, which you have to formulate using a huge number of ODEs, actually the system can be summarized into, it's kind of like a reverse case when everyone is talking about dimension reduction. Actually, this problem is very complicated. It's difficult to solve. Maybe the mentioned group affiliation approach potentially can help solving this one. But we also have a numerical scheme, adaptive dynamics, can solve this ones.
What about the integral? You have integral with respect to what? Because you told that.
With traits, with traits.
Yeah, but you told that they are changed, so space is changed. How do you involve this?
Traits, this is the integral over all the entire trait space. So that's why the computational is very heavy. Whereas the previous version is, I just, yeah.
It's changed now, it's not changed, right? S of t was changed, and the integral must be with respect to S of t, right?
Which one, sorry?
ST, before you follow the ST, space is changed. So space of X.
Where is the set S?
Yeah, no.
Oh yeah, the set.
Set, yeah.
So this model, what this model numerically implement is it will generate multiple peaks.
From minus infinity to infinity.
Yeah. I can just show one simulation. This is very similar to this type of simulation. Okay, so at least we know the ODEs and the PDEs. So this is one of the simulation you can see. It doesn't change. It's not going to the place. Okay. So it's essentially we are looking at NXT, and the T is a snapshot. Yeah, this is just T, and this is X. And those situation is in the simulation of that integral differential is multiple peaks.
But you took a particular class of functions, right? So
Yeah.
what kind?
It depends, and when you change the kernel functions, you're going to have very different patterns. Yeah. So what I'm saying is, I'm trying to get the interpretation right. So this is using ODEs. We're doing this. The problem of this challenge is every time when bring in a new species, or every time there is an evolutionary branching, we need to add a set of equations to indicate that one's population dynamics and the trait dynamics. So that species set is keep changing. Whereas using the last page, that integral difference equation, we don't have. It's just part of the solution. It's a multimodal solution. So if we can solve that,
It's complicated because it's appearing new.
Yeah.
And this is like shock waves, special point. Not analytical.
yeah, those are continuous, differentiable, those points. Yeah. So the peaks is not this peak, it's smooth peaks, yeah. Okay, I'm gonna numerically, yeah. That's why I'm thinking if we can use group affiliations or symmetry analysis to have a full set of solutions of this co-evolving system. And that's the core for collaboration. Thank you.
We have maybe 3 minutes for questions.
So every next set was removing something from the previous one and adding something new.
Yeah.
Is it not interesting to consider also the case where 2 elements in the previous set merge into one, or when a single element splits into several?
You can have a single split into 2. but you can't. So that's a ecological relevance. You don't have hybrid normally doesn't.
But even single splitting into two, that's not captured by the formalism you gave, right? Because
No. We do have this. So this
no,
is
but
this is a singularity point.
But in the description of the sets that you gave, SI plus 1 equals something out of SI.
Yeah.
That information wasn't kept there.
Yeah, there needs to be a condition, and we know that condition. We have to evaluate that condition. If the condition is satisfied, ST is equal to ST plus 1 is equal to ST plus 1, or just add that space.
Okay.
So you can add those things into your system.
Thank you.
Yeah. Okay. Yeah. It's a hard topic.
Just clip this one. Second one.
Okay.
Okay, the next talk is from Professor Luca, Symmetry Summer School, SU, sorry, Diophantin what sets. Professor, you can take over. Sorry.
Thank you very much. Well, thank you very much. I thank the organizer for organizing this great school, and I have nothing to do with the topic of the school. So I will start by telling you why I'm here. So I'm a professor at WITS, but I hold a fellowship at STIAS, which is the place that organized the Nobel event yesterday. So they may have many activities. One of those is hosting fellows, and I encourage the people here to apply for fellowships there. It's a very nice place. And as I was applying for a leave from my boss, Professor Kara, that sits there in the back of the room, he said, "Oh, you're going to be in Stellenbosch for a few months. You should go and introduce yourself to Professor Sibu." And me being a shy guy, of course, I didn't make any attempts. But since STIAS organizes many nice things, at one of the public lectures, Professor Sibu came there. And after the public lecture, we had some wine and some snacks like yesterday. So I worked up the courage and I went there and I did what my boss from Johannesburg told me to do. And I introduced myself to Professor Sibu, and she said, "Oh, you're a mathematician. That's great. You have to give a talk at my conference, and I expect your abstract by tonight." So I was preparing my my talk for STIAS. In STIAS, as I said, those fellowships are very interesting because unlike, let's say, the Institute for Advanced Study in Princeton or these institutes from the Max Planck Society, where you kind of see the people that do the same thing as you do, there all these fellows are from different backgrounds. We are only two mathematicians. There's political scientists, there's artists, there's writers. And one of the things that we have to do, we have to give seminars to these people. And they have to understand what we are doing. So basically I was working on that. So I said, "Oh, this is great. Like these people are mathematicians. I can extract a small portion of that and maybe put a little bit more details in it." And that's what I'm going to do. So I'm going to tell you about Diophantin sets. What are those guys? Well, there's this guy, Diophantus of Alexandria. He was a mathematician. He's referred to as the father of algebra. And he was born around 200, probably in Alexandria, and he died around 284. And as I said, he was referred to as the father of algebra. So one of the things that he left behind, he left a collection of books, which is called Arithmetica. In this collection of books, he was collecting sort of numerical curiosities. One numerical curiosity that he was collecting numbers with the property that if you multiply them and you add them, you get perfect squares of some other numbers. For him, a number was a rational number. For some reason, those old mathematicians, they liked rational, they didn't like integers. Like when we talk about Egyptian fractions and so on, they were always things like 1 over an integer. So for example, here's a collection from him. So those numbers, 1 over 16, 33 over 16, 17 over 4, and 105 over 16 have the property that if you multiply any two of them and you add 1, you get a square of some other fraction. For example, the first calculation is 33 over 256 plus 1 is 289 over 256, which is a perfect square. Of course, he didn't say anything, how he found them or why he found them interesting and so on. But you can generalize that. You can say, well, let's, in his honor, this is why we call now Diophantine equations. They are equations that have solutions in integers. So you guys work with equations that have solutions in functions. And since you have solutions in functions, then your equations have a much richer structure because those functions, you can differentiate them, you can integrate them, you can do things with them. We only have the numbers to work with them. There's not so much we can do with them. But you can ask about, for example, you can call a Diophantine tuple to be a set of elements in some ring, such that the product of any two of them plus 1 is a square. And then one of the problems of interest would be, well, can you find those things in, let's say, Q? Can you find infinitely many of them? Can you find the ones that have integer components? Can you find examples with 5? Can you find examples with 6? So these are the kind of questions that people have been working on. And Pierre de Fermat actually liked Diophantus's book a lot. He was always reading it. And there is that statement that we learn in mathematics about Fermat's last theorem, which is this theorem that the sum of two nth powers is never an nth power if n is greater or equal to 3. And the anecdote is that he could write the proof of this statement on the margin of some book. Well, that book was Diophantus's book. This is what he was reading. And he noticed that 1, 3, and 8, and 120, it's an example like that, with integer components. You can ask, are there infinitely many with integer components? And yes, they are. For example, if you take those 4 polynomials and you multiply any two of them and you add 1, you get a square of another polynomial. If you make k equal to 2, you get Fermat's example, which is 1, 3, 8, and 120. So what this example is, it's an example of a parametric family. Now there's other ones which grow exponentially with Fibonacci numbers. We all know Fibonacci numbers. They start with 0, 1. It's maybe the simplest evolutionary model, right? Because you start with a pair of rabbits in some field and they multiply according to some rule. And then you notice that, that those guys, if you take the Fibonacci numbers of 3 consecutive even indices, and then you slap on that quantity there, then it turns out that the product of any two of these things plus 1 is a square. And these things you can kind of give them as little exercises to your students to prove that the product of these two guys plus 1 is a square, and so on. And if you make n equal to 1, what do you get? You get the second Fibonacci number, which is 3. You get the which is 1. You get the fourth one, which is 3. You get the sixth one, which is 8. And so basically this example that I showed you, it lives as sort of the starting example of these two parametric families. And there is some little symmetry in there. Suppose that you have 3 integers with the property that they, actually it's something about rings. You have some commutative structure, like a commutative ring, and you take 3 guys in there such that the product of any two of them plus 1 is a square. If you live into the integers, what you can do, you can multiply those 3 squares. And of course, if you multiply those 3 squares, you're going to get a square. But in the integers, what's true is that if the product of these 3 things is a square, then each one of them is individually a square. This is a little exercise. You prove it around. You just manipulate some things in there. What is even more interesting is that suppose that you want to add a 4th element to it. So you already have 3 of them, like 1, 3, and 8, and then you want to add a 4th element. Then what you're going to do, you're going to say, let me look for a number d such that these 3 expressions are squares. Well, it turns out that this always exists. Well, first of all, you can eliminate the number d. You don't know what it is, but it's linear. Those equations are linear in d. but somehow this D appears in 3 places. So you can eliminate them from the first 2 and last 2, or from the first 2 and the first and the third. And you get 2 things like this. So you get some equation, A, B, and C are fixed. You get some quadratic in here, X and Y. These things usually, if they have a solution, which they do, because they always have the solution 1, 1, they have infinitely many solutions. And they grow into like a binary recurrent sequence, which is what you guys do when you do sort of ordinary differential equations of degree 2, and you associate a quadratic polynomial and you solve it and so on. This, the technique is a bit similar. But now you have 2 guys like that, and you ask them for a certain component to be common. And these things end up having only finitely many solutions. Now, if the example of Fermat, then in 1, 3, and 8, then you want to find D such that D plus 1, 3D plus 1, 8D plus 1 are squares. You write down this, you eliminate them, you get this system of, it has 3 unknowns and only 2 equations, but they appear in squares, and the only such is 120. Now, here is something that some people noted. So suppose that you go back to that example, AB plus 1 equals the square of R, AC plus 1 the square of S, BC plus 1 equals the square of T, and you construct D given by this formula, then it turns out that this D is the 4th element. So every time you have 3 of them, you have 4 of them. And it's giving it to you for granted. Basically, you just manipulate these things and they work. So let's call things, nobody knows of a Diophantine quintuple. Nobody knows of an example of 5 positive integers such that the product of any 2 of them plus 1 is the square. More than that, the only examples with 4 that are known are given like this. So it's always the case that the 4th element is obtained in this way from the first 3. So of course, since the mathematicians like to make conjectures, so what conjectures can we make? We can make a conjecture where there is no such set with 5 elements. We can make a stronger conjecture that all such sets with 4 elements are regular in the sense that the 4th element is given in terms of the first 3 by that formula. So why is this one stronger? Well, because if this one is true, then of course you can't have 1 with 5, because if you have 1 with 5, you take the first 3 of them, and then we look at the first 3 and the 4th one, and you look at the first 3 and the 5th one, and they are both quadruples. But this can't exist because all the quadruples are regular. So the largest one is given in a unique way in terms of the first 3. So the weak conjecture has been proved in 2019. The strong conjecture is still open. And then the strong conjecture is known in some cases. So if you go to parametric families like this, it is known that for those kind of things it works. So if you have A, B, and C being K minus 1, K plus 1, and 4K, then the 4th element, if you try to add a 4th element there, then it's always that one. There's no other element like that. And then also for the Fibonacci numbers is known that they are regular. Now, what about, let's go to the rational case. In the rational case, it's not even known that the length is absolutely bounded. So it's known that you can't have an infinite set of fractions such that the product of any 2 of them plus 1 is a square, but it's not known that you can't have sort of very large ones. That is not known. There is conjectures, we like to conjecture things, and you always throw in some names like the Riemann hypothesis or whatever. So under certain conjectures, then we believe that these things are bounded, but it's not known. Well, what is known? Well, Euler was one of the most prolific mathematicians in history. He wrote like more than 800 papers. He was very different from Nash, I guess. And Euler had something to do with it. So Fermat stopped here, and Euler found out that that fraction, if you take that fraction and you join it in there, then the product between that fraction and any one of those 4 integers plus 1 is a square. Amazing that he found that. Actually, it's a recent result of just a few years ago that that's the only way. If you're looking for a rational number such that, let's call it x, such that x times each one of those guys plus 1 is a square, then the only such x is, of course, x equals 0 works, but you don't want it. The only such x is that one. Then there's examples with 6. Like here's an example of 6 fractions such that the product of any 2 of them plus 1 is a square. Infinitely many examples with 6 are known. No example with 7 is known. So maybe 7 is, maybe 6 is the largest, but nobody knows. So what's next? One of the things we could try next, rational numbers are complicated. We like integers more. We believe that the integers are easier. So you want to go from a rational number to an integer, then it kind of makes sense to say, instead of shifting it by 1, let me shift by some number n. Because then the problem becomes from the rational numbers, you can move to integers because you put these rational numbers to the common denominator. When you multiply two fractions, the common denominator becomes square. You can multiply that square across and incorporate it into this one. And this is the square of the common denominator. And then you can replace it back. So you can say, well, what can we say about this problem? Well, in this problem, you can find the bound of m in terms of n, but you would like to find the bound of m in terms of n, which is independent of the number n. That is not known. You can find bounds versus m versus n. If you just want to find some bounds, then, for example, here is the result of 2005 of a colleague, Andrei Duela. He's a mathematician from Zagreb. And then here is some contribution that I did a long time ago. I said, let's take n to be a prime number. If you take n to be a prime number, then we found some bound which is independent on the prime number n, on the prime number p. Now, if you could remove this p from here, and you could replace it by any integer, then you would get an answer to the, well, there are no arbitrarily large things like this of rational numbers. And of course, this one is some ridiculous bound, as we the mathematicians prove it. Because in mathematics, when you try to prove a result, for example, before proving that every large integer is a sum of 3 primes, I think, which is odd, I think the result was that every large odd integer is a sum of 1001 primes, which you say, oh, okay, that is interesting, but still computational it's. So this is a little bit like what we have there. And this number comes from some part of graph theory, which is called Ramsey numbers, which grow very fast. So our proof sort of associates some graph theoretical structure to it. And inside that graph, you have some equations and you have some sort of monochromatic property, and you looked up some Ramsey number and it gives you that. All right, so our method also gives a bound on m when n is square free. And for example, if n is a square free integer with at most 10 primes, then it's going to give you a huge bound in here, but it's gonna be like a tower of exponential of size 10 or something. All right, so so I went a little bit fast through it. You now have a longer coffee break. And
Okay. Mrs.
Thank you so much for a very, what you say, interesting and short to the point talk. I just wanted to find out, so in this area now, so what will be the next Nobel Prize? What is the problem that has to be dealt with for somebody?
Well, there is something called the ABC conjecture, which there's a group of mathematicians in Japan which believe that one of their colleagues has proved it, but there is no consensus about that. There's other groups that kind of looked through that proofs and they believe that maybe it's not entirely correct and so on. So the ABC conjecture is something that is trying to relate the additive structure to the multiplicative structure. So of course, if you multiply 2 squares, you get a square, but if you multiply 2 numbers with lots of small primes in there, you get an answer with lots of small primes. But now the question is, can you add 2 numbers with lots of small primes in them? And the answer is still a number that has small primes in there. And this ABC conjecture is trying to reconcile that, and it's trying to say that, no, you can't do that. And if that conjecture is true, usually it gives you short proofs of the fact that maybe Fermat's last theorem should have only finitely many solutions. And there is things beyond Fermat. So Fermat's last theorem is about the sum of 2 nth powers equal an nth power. Then you can ask, what about the sum between x to the power a plus y to the power b equals z to the power c? So you take 3 different powers and you impose some coprimality conditions. It turns out that if the sum of the reciprocals of these exponents is bigger than 1, you always have solutions, like x squared plus y squared equals z squared. But if the sum of the reciprocals is smaller than 1, then it's believed that you have only finitely many solutions, even with the exponents running around freely. But this is only known for particular triples of exponents. For example, the sum of two cubes is never a fifth power, or things like this. So these are, let's say, big questions in the area of Diophantine equation.
And what's your sense with these AI, applications? Do you think that? So we were just talking at lunchtime about some problems, and some of our colleagues suggesting like you can just put this and then you.
From what I have
some ideas. What has been
heard talking to colleagues, I have no feeling about that. But from talking to people, I have not seen that AI has made any contribution to the field. But AI will probably, if you feed it all the literature that has been written in the world, then probably AI would be useful for references. You could tell AI, why don't you go and look in the literature and see if somebody might have studied this equation? And since it already has all the database in it, then it can say, oh, such and such did this, and here's their results, and so on. So in that sense, it could be useful as a tool. But making AI prove a statement, making those steps inside the deduction, I have not seen that yet.
So there's no guarantee that AI can win the prize, Nobel Prize.
But it also depends what is a proof. Like if you want to deduce some identities from a different identity, maybe you can, if they are polynomials, you can feed it some Grobner basis and you can see if that identity sits inside that the ideal generated by those things. But